Planet Earth. 4.5 billion years old. A solid ball of rock weighing 6 trillion tons. We are on a quest to destroy it. Using cutting-edge physics and planetary science, we will explore what could destroy our planet completely. A black hole?
It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth.
A collision with the sun?
And before you know it, the Earth is falling into a fiery plummet.
A huge antimatter bomb?
Poof, okay, at a huge annihilation.
A giant rock from space?
You wouldn't want to be standing here 50,000 years ago.
Or perhaps a swarm of self-replicating robots.
It's been a nightmare of sci-fi.
These ideas may sound like science fiction, but they're all grounded in proven scientific fact. Our planet is seriously tough. It has survived everything a hostile universe could throw at it for 4.5 billion years. Yet in the past few decades, we have developed technologies so powerful that some people fear we could literally destroy the Earth. It's time to find out if they're right. 6 top scientists are about to reveal what it would really take to destroy an entire planet. Our first candidate is a black hole, the greatest destructive force in the universe. A black hole is what's left when a giant star collapses in on itself. The result? Gravity so strong that nothing can escape, not even light. Soon, we may be able to create black holes right here on Earth. Physicists use huge particle accelerators to try to recreate what happened after the Big Bang. But when they smash particles together, they also risk creating a black hole. Think of a black hole as Niagara Falls, and the water going over like space getting sucked in. This unfortunate kayaker has gotten too close. Just like a star getting too close to a black hole. Dr. Phil Plait, astronomer and author.
The water going over the lip of the waterfall is just like space itself falling into a black hole. If you're kayaking, no matter how fast you paddle, once you go over that lip, you're going down. That's the point of no return. And it's the same thing with a black hole. No matter how fast you try to get out, it's going to take you down.
The gravity in a black hole is fundamentally different from the gravity we experience in normal life. Normal gravity you can escape from, at least in theory. Cosmologist and golfer Professor Lawrence Krauss.
It's commonly said that what goes up must come down, but that's not always the case. For example, if I hit this golf ball here and I hit it well, it would go fairly far, but it would still come back down to Earth. If I hit it harder, it would go further and still come back down. But if I hit it with a speed of 5 miles per second, it would escape from the Earth's gravitational field.
But for the ball to escape from a black hole, it would have to move faster than the speed of light, and that is simply not possible. What goes into a black hole, planets, or even stars, never comes out. Our small planet wouldn't stand a chance. For anyone looking for a way to destroy the Earth, black holes are a good place to start. The trouble is, there are none close by enough to do the job. Unless we make one. That's where the atom smashers come in. With a lot of math and a gigantic machine, physicists can now generate atom-sized explosions that may be powerful enough to create microscopic black holes. They are trying to study the Big Bang. The force of the impacts recreates the particles that made up the universe in its earliest moments. Some of those particles may create microscopic black holes. That doesn't mean our planet is doomed. In theory, black holes this small would just evaporate like tiny soap bubbles. To destroy this, you need something bigger.
Black holes come in all sorts of different sizes. For example, at the center of our galaxy, there's a black hole of 1 million solar masses. If you took the mass of our sun and compressed it down to be a black hole, it would be the size of a large American city like Phoenix here. On the other hand, if you took something like this mountain here, which is maybe 1 million tons, and made it a black hole, it would be smaller than the size of a single atomic nucleus.
Somewhere along that scale, black holes get powerful enough to cause serious damage. To destroy the Earth, it turns out you need a black hole that weighs about the same as the Earth. The Earth is 8,000 miles across. But a black hole weighing that much would be the size of a marble. Professor Clifford Johnson, physicist.
Here I have a marble-sized black hole. It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth. What would eventually happen is that it'll start sucking things in, slowly at first, and then it will grow in size. It will grow and grow and grow until it swallows the whole Earth.
To imagine what that marble would do to the Earth, picture what it does to a physicist.
The gravity is much stronger on one side of an object closer to the black hole than it is on the other side of an object, producing an effect that's called spaghettification, as that object is stretched out and pulled apart as it falls into the black hole.
A big enough black hole could do this to our whole planet. There's no way even the most powerful atom smasher could make a black hole this big. To destroy the Earth, we need to find one ready-made. Astronomers think there are 10 million or so black holes in our galaxy. If one of them strayed into our neighborhood, it could rip our planet to pieces. Earthbound telescopes may not even detect it. Humans would only know it was approaching when its immense gravity triggers huge floods and earthquakes. As it plunges into our atmosphere, the black hole acts like a vacuum cleaner, sucking with a force over 1,500 times Earth's gravity. Then it begins to distort the shape of the whole planet. Earth's surface stretches and tears apart. Finally, the hole hits and flies straight on in, heating and vaporizing matter as it goes. It starts to orbit the Earth, inside the planet itself, all the time devouring everything in its path. Gradually, the orbit slows. The black hole spirals down into the Earth's core. Eventually, it eats the entire planet. All that's left is the black hole itself. It's a devastating end for planet Earth. But fortunately for us, it's unlikely ever to happen.
If you want to destroy a planet, a black hole is a great way to do it. But the problem is, it depends on the kind of black hole. A microscopic black hole would just pass right through the Earth, and it really wouldn't do that much damage. A black hole with the mass of the Earth would be about the size of a marble, and that would do a considerable amount of damage passing through the Earth. But again, it might not destroy the planet. If you want to do the job right, you need a stellar mass black hole, something with about 3 times the mass of the Sun. That thing would come in and it would tear the Earth apart and gobble down the pieces, and it would be game over. The problem is, we don't know how to make any of these black holes. Technologically, we just can't do it. And with a naturally existing one, we don't know how to move them. So there's got to be a better way.
So if black holes don't work, time for a new approach. One surefire way to destroy the Earth is to change its distance from the Sun. Move the planet closer and it bakes. Move it out and we freeze, sending us into another ice age. Scientists have recently begun to realize that moving a whole planet might actually be possible. In fact, we use the same principle to slingshot space probes round the solar system. Planet Earth could be just a few well-placed flybys away from a fiery death. What would it take to incinerate an entire planet? Answer: a nuclear furnace nearly 1 million miles across. It sounds crazy, but the truth is this will happen. It's just a matter of time.
As the sun gets older and older, it's going to actually get brighter and brighter. And within about 2 billion years, the Earth will be in an uninhabitable zone. It'll be like Venus. There'll be a runaway greenhouse effect. All the water on Earth will be destroyed, and the surface temperature will be about 1,000 degrees.
Eventually, the sun will swell and scorch the Earth, unless we somehow move the Earth away from the sun to save it.
Alternatively, if you were sufficiently evil, I suppose, you could imagine doing exactly the opposite. Harnessing sufficiently large objects to transfer gravitational energy to kick the Earth's orbit closer to the sun.
Easy to say, not so easy to do. The Earth weighs in at 6 trillion tons. Pushing something that big is quite a challenge. But there is a way. It's called gravity assist. Space probe engineers use gravity assists all the time. Take Saturn's Cassini-Huygens probe. It's the size of a school bus, one of the biggest probes ever built. To build up enough speed to fling the probe out to Saturn, it had to swing by Venus twice and Earth once. Each flyby stole energy from the planet and added it to the probe. The probe got a lot faster by altering the planet's course just a little.
The name of the game, we take a rock about 1 mile or 2 across, and we move it so that it just passes the Earth the right way, and it'll steal energy away from the Earth. The asteroid will go flying off, and the Earth will move in toward the sun. But we shouldn't just waste the asteroid when we can recycle it. If we're clever, we can take the asteroid and have it go toward the planet Jupiter. And then if we pass Jupiter in just the right way, it'll take that extra energy it stole from the Earth, give it to Jupiter, and then fall back toward the Earth. And if we aim everything just right, we get a conveyor belt of energy. We steal it from the Earth, give it to Jupiter, and then come right back. And in fact, we can use hundreds or even thousands of asteroids this way, continuously stealing Earth's energy and dumping it toward Jupiter. And before you know it, the Earth is falling into a fiery plummet.
First, you need to catch an asteroid. It's as big as a mountain, and it's traveling around 10 miles a second. Next, you need to attach rockets and boost the asteroid onto the perfect course. Next, repeat, thousands and thousands of times. Very slowly, over thousands of years, the Earth will fall towards the Sun. Right now, we're just over 90 million miles away. By 70 million, the Earth is a superheated desert like Venus. Then things start to get really bad.
As the Earth slowly spirals into the Sun, a series of events unfolds which unfortunately spells doom for our planet. As the Earth approaches the Sun, the atmosphere heats up and blows off, and the oceans boil, basically turning the Earth into a giant comet. But there's worse to come. As the Earth gets closer to the Sun's gravity pulls on the near side of the Earth more than it pulls on the far side, and the Earth stretches like putty. At some point, it gets close enough to the Sun that the Sun's gravity can overwhelm the Earth's gravity, and it shatters, pulverizes our planet.
The Earth is dead, but its ghost could remain, a faint ring of material around the Sun. Peter Schultz, planetary impact geologist.
If the Earth or any object gets too close to another object like the Sun, eventually the tides will rip it apart. As that happens, it would simply be broken into many small pieces that would then encircle the Sun as if it were a ring.
The Sun would resemble Saturn with its own faint ring of rocks and dust. A fiery death and a ghostly remnant. If you want to destroy a planet, this could be the way to go.
A great way to destroy the Earth is to drop it into the Sun, let it plummet to a fiery death. And we can do this. All you need to do is to pass enough asteroids near the Earth in succession to gravitationally drop it into the Sun. And we have that technology. We know how to move asteroids. It's just a matter of getting them on a precise enough orbit to be able to do it.
Maneuvering billion-ton chunks of rock with pinpoint precision at hundreds of miles a minute is quite a stretch. Not to mention the amount of time it would take to capture enough asteroids. We've tried to crush it and burn it. It's time for another plan. An antimatter bomb. Physicists have been searching for over a century for a theory that unites our understanding of the large-scale universe, planets, galaxies, and stars, with what we know of the subatomic world, electrons, protons, and quarks. Their theories are bringing to light some pretty destructive phenomena. One of them could be a world killer. Antimatter. Theorized in the 1920s, detected in the 30s. Now we can create antimatter in modern particle colliders. And the base ingredient for the biggest explosion possible. Antimatter is the most explosive substance ever found. Pound for pound, it's far more powerful than even a hydrogen bomb. But antimatter is hard stuff to find. Everything we see around us, out to the most distant galaxies, is matter, created 13 billion years ago in the Big Bang. It created antimatter too. They look similar. In fact, they are entirely opposite. Put them together, and they wipe each other out. Cosmologist Lawrence Krauss.
Now I have a proton here, and anti-Krauss over there has an antiproton. And when we bring them together, we're going to make an incredible explosion. Okay, let's annihilate.
This is what happened to all the antimatter created in the Big Bang. It annihilated. If we want to use some for a bomb, we need to make it ourselves. Making antimatter is a bit like firing a gun at a target.
If I shoot a gun at a paper target, the paper that flies out of the target is like matter, and the hole that's left behind is the antimatter. It takes energy to create a matter-antimatter particle pair. In the shooting range analogy, the bullet provided the energy.
In reality, the gun is a particle accelerator, like the one at CERN in Switzerland. Fire protons in a giant tube, steer them around with powerful magnets, use the same magnets to accelerate the protons to near the speed of light, then slam the beam into a block of metal. For every million protons that hit, you get one antiproton. It's as if Plate's handgun only left a hole once in every million shots.
In an accelerator, you only get one particle-antiparticle pair out of every million collisions or so. And so it's really hard to find that one antimatter particle floating around. It's a lot like coming to Niagara Falls and trying to get that one particle out of all the mist. And that's why it's so hard to create antimatter on a large scale.
Assuming we can obtain enough antimatter, the next challenge is to make it into a bomb. Nothing is more unstable than an antimatter bomb. You have to find a way to hold the antimatter without it touching any ordinary matter. If it does, it will explode.
So I have a bunch of antimatter above my hand here. Well, it better not touch my hand, because if it does, poof, okay, at a huge annihilation. But worse, it can't interact with the air around it, because the air is made of matter. And again, you'd get an incredible explosion.
Researchers need a special container to study antimatter. And this is it, a penning trap. Powerful magnets suspend the antimatter in a vacuum.
So if I want to store this antimatter, what I have to do is somehow keep it levitated above my hand, which means I'd have to produce huge magnetic fields in just the right way to keep the charged particles in the antimatter from touching my hand. But I'd also have to store it in an incredibly high vacuum, because any air in the container would again cause an explosion. And so the energies and technology required to produce those magnetic fields, keep that ultra high vacuum, would mean that you wouldn't have a small object. You'd have to have surrounded with massive amounts of machinery.
Yet for all that trouble, an antimatter bomb isn't just theory. We can make antimatter, we can capture it, and we can store it. But where do we plant it for maximum effect? If we want to destroy the whole planet, the bomb has to go off near the Earth's core. That's nearly 4,000 miles straight down, further away than London from DC. Right now, that's impossible. The deepest man-made borehole stops at just 7.5 miles. But what if we could? So far, mankind has managed to create a grand total of 20 nanograms of antimatter. That's 100 million times lighter than a dime in your pocket. So the bomb is going to be too small even to see.
Well, 200 feet away in this test range in Arizona, we have the explosive equivalent of TNT. So let's see how big of a bang that makes. Wow.
20 nanograms of antimatter makes quite a blast, but it's way short. To destroy planet Earth, we would need 2.5 trillion tons of the stuff. That's a bomb the size of Mount Everest, at the bottom of a hole 4,000 miles deep. If it were possible, the result would split the Earth into thousands of pieces. With a powerful enough bomb, the pieces would fly out into space and are lost. With a slightly weaker bomb, the pieces fall back under the force of their own gravity, collapsing into a molten ball. An eerie echo of Earth's creation 4.5 billion years ago. It could happen, in theory, but there are a few technical details to iron out first.
So what's the matter with antimatter? Well, if you're trying to destroy the Earth, it'll work, it'll do the job. The problem is you need about the energy that the sun puts out in an entire week. So it's a huge amount, and we just don't have the technology to create that right now.
At the present rate of production, making the bomb would take more than the age of the universe.
The other problem is getting it to the Earth. How do you do that? Well, you'd have to get it to the center of the Earth, and that means digging a hole several miles across and 4,000 miles deep. So in the end, don't think antimatter is probably the most efficient way of destroying the planet.
So, as a way of destroying the Earth, maybe antimatter has some problems. But we know the next approach works, because it already happened once before in Earth's ancient past. Space is a dangerous place. It's full of debris. Rocks the size of pebbles, up to rocks near the size of a planet. There are impact craters everywhere, including our moon. These asteroids can hit us as well. An asteroid wiped out the dinosaurs. Maybe a bigger asteroid could destroy the planet entirely. Meteor Crater, Arizona. Almost a mile across, nearly 600 feet deep. Today, science can reconstruct what happened here thousands of years ago. Dr. Dan Durda, planetary scientist.
You wouldn't want to be standing here 50,000 years ago. This iron meteorite, about the size of a small office building or so, it's made out of stainless steel from space. It's about to strike the desert with an impact energy of somewhere between 1 and 10 megatons. And it's that energy that's going to excavate and open up this crater behind me, which is nearly a mile across.
The impact ultimately devastated an area the size of New York City, with 600 times the power of the Hiroshima bomb. And that was small. 65 million years ago, a real monster struck. It was 6 miles across. Sat on the ground, it would outtop Everest by half a mile. The crater was over 100 miles wide. The impact wiped out the dinosaurs and destroyed most of life on Earth. An even bigger space rock could destroy the planet. We're already developing technologies to protect against future impacts. Ironically, you could use those same technologies to make an impact happen. One approach is to hover a space probe near the asteroid. The probe's mass generates a tiny gravitational pull on the rock. Over time, that can change the asteroid's course enough to miss the Earth, or to guarantee a hit. Another protection technology that we could use is a technique called solar sublimation. This diverts an asteroid or comet using nothing more than sunlight. To demonstrate the effect, Dirda starts by building a homemade comet.
Some fraction of near-Earth objects are comets, so let's examine what comets are made of. Let's actually make a comet.
Take some soil, add dry ice, then water, and some chocolate.
We'll put in a few percent of organic material into our comet. And of course, in the outermost solar system, there's a little bit of ammonia here and there. We'll let that be represented by this ammonia cleaner. Let's see if we can pack this up and make ourselves a little comet nucleus.
A magnifying lens completes the apparatus.
If one were to actually focus the light from the sun onto the surface, one could cause some of that water to vaporize away. And just like on this comet nucleus, the jetting action of those evaporating gases act a little bit like little artificial rocket motors attached to the object. And over time, they really do cause it to be pushed slightly off course.
The power of sunlight alone is enough to divert a space rock onto a collision course with Earth. But solar sublimation may not be effective on an object big enough to pulverize our planet. To destroy the Earth, our space missile needs to be big. Like Mars big. We know this for certain because it's happened before. 4.5 billion years ago, a rock the size of Mars struck the Earth a glancing blow. The impact debris created the Moon. If it had hit head-on, none of us would be here. We've come here to the vertical gun range at NASA Ames in California for proof. This 12-foot gun fires beads up to 4 miles per second, 6 times faster than a rifle bullet. Professor Peter Schultz, a planetary impact geologist, uses the gun to simulate a Mars-sized object, represented by this small projectile, hitting our planet head-on. The space environment chamber is ready. Schultz makes his final adjustments. But will our scale model Earth break apart completely?
That hurt. That really hurt. Look at this thing, this is worse than a science fiction movie. That's just glorious disaster. There's nothing left.
A head-on strike, destruction guaranteed.
So the things that destroy an object is going to be a combination of the size of the object, the speed of the object, and the angle. The lower the angle, the less likely it'll completely bust it apart. So to really destroy the Earth, you need something that's humongous and needs to hit straight on.
Now we know what it takes to use an impact to destroy planet Earth. Asteroids and comets are just too small. We need to move something the size of a planet onto a collision course. That's a level of technology we won't be reaching anytime soon.
Now, we can move asteroids around and we can move comets around, but those are only a few miles across. The problem here is that we need something really big. Mars is about a third of the size of the Earth, and even that hitting the Earth won't destroy it. We would need something almost as big as the Earth itself, something like Venus. And even then, we just don't have the technology to be able to move something that big with that kind of precision to aim it at the Earth and blow it up.
Destroying the Earth with a space rock just isn't gonna happen. Perhaps the killer punch won't come from space, but from right here on Earth. Genetics, robotics, nanotechnology. Researchers hope machines will lead us to a brave new world. Already, robots can learn, build other robots, and cooperate with each other. It could be the beginning of a new age. It could also be the beginning of the end. Right now, we can only build robots that work with humans in control, but science is working towards machines that can think for themselves and even reproduce. Robots that can make copies of themselves without human control could one day take over the world. Hod Lipson, professor of robotics. Lipson is a pioneer in robot replication.
If this robot could make another robot identical to itself, and then those two robots can make 4 robots and so forth, these robots could fill up a space such as this here fairly quickly.
Once the first replicate is made, there's no stopping the process. But first, we've got to make them. At Cornell's robotics lab, Lipson and his team already make robots that learn, robots that build, and robots that build themselves. This is the world's first self-replicating robot. Supply it with building blocks and it assembles them to make a copy of itself. It needs Lipson and his lab techs to keep it stocked with plastic cubes. So this robot is pretty benign. To destroy the Earth, we need to develop robots that use smaller blocks and eventually individual atoms.
We've been trying to make robots made of much tinier cubes on the order of 0.5 millimeter. You can barely see them. There's about 10 of them in this container here. We're trying to get these very small units to combine together, and the smaller they get, the faster and more easy it is to replicate.
Lipson thinks that advances in robotics will revolutionize design and manufacture. But where there's progress, there's also danger. In theory, nano-sized machines could start to replicate out of control. Self-replicating nanomachines could, in theory, destroy all life on Earth. To destroy the planet itself, we need something more. To reproduce, a robot needs energy and raw materials. In other words, food. The more food there is, the more copies our robots can make. And the biggest source of food on the planet is the planet itself.
The ultimate kind of self-replicating process is something that's inspired by nature. So if we can have a machine that can essentially self-replicate using resources in the environment, food and energy, then that would be a pretty big achievement.
And the biggest natural resource on Earth is rock. Design a self-replicating robot that feeds on rock, and it has 6 trillion tons of food right under its feet. Some living creatures already use rock. Rock-feeding bacteria live in the Earth's crust, even several miles deep. But nature's rock eaters are good for the planet. They help form soil and keep life ticking.
There's a whole suite of rock-eating bacteria that we've now uncovered on the Earth, which will go and chew up and eat and use the materials in the rocks for their sources of energy and for the sources of compounds they use to build other biologic molecules. There are literally biologic organisms that do just this, eat rock.
Rock-eating, self-replicating robots. But they've got to be smart. They need to cooperate. Professor Alan Winfield, roboticist in charge of the Symbrian project, to design robots that swarm like insects.
Symbrian is a 5-year project to try and build a swarm of self-assembling robots. Perhaps as many as 30 or 40 will physically join and then behave and act as a single organism. The big challenge is going to be how to get the robots to first of all decide what to be: a foot bot, or a knee bot, or a sensor bot, or a brain bot, and then work cooperatively so that, for instance, the organism can stand up and walk.
We can already make robots that reproduce. We can make robots that cooperate. Put them together, and at last we may have our planet killer. Here's the math. Say each robot takes 1 day to replicate. Then after a single month, you have over 1 billion robots. After a year, you have trillions. Earth is covered with machines that do nothing but gobble rock. In the end, no more rock, just a huge ball of self-replicating machines.
Now, what are robots made of? Well, iron, magnesium, aluminum, and silicon. The same thing the Earth is made of. And so all you have to do is create one of these self-replicating robots and let it out into the wild. It'll make a zillion copies of itself, and they will consume the Earth, and eventually there'll be nothing left.
Success at last? Perhaps not. In our quest to destroy the planet, we've tried devouring it, incinerating it, pulverizing it, blowing it up, and breaking it down. Planet Earth is a proven survivor. It has taken everything the universe can throw at it for 4.5 billion years. And one thing is certain: we're still here.
Venus, Earth's evil twin. Its clouds made of battery acid. At 900 degrees, its surface hot enough to melt lead.
Venus is pretty much like the biblical vision of hell today.
This may be the most hostile real estate in the solar system. Yet billions of years ago, Venus looked a lot like Earth. Why it changed, nobody knows. A new probe is on a mission to find out. What turned Venus from a promising Eden into an infernal wasteland? And is Earth destined to end up like Venus? November 9th, 2005. A Russian Soyuz rocket launches from Kazakhstan, carrying a tiny European spacecraft called Venus Express. Its mission, to travel the 250 million miles to Venus and find out why the planet evolved so differently from Earth. For centuries, Venus's surface remained an enigma, obscured by layers of dense clouds. Because Venus is closer to the Sun than Earth, scientists assumed it would be hot and humid. Some even imagined a tropical paradise. The perfect hothouse for life.
Venus should be about the same temperature as the Earth. And that's what we thought back in the 50s and early 60s. We thought Venus should be like Miami, Florida.
What was really going on beneath the clouds? In the 1960s and 70s, while NASA explored Mars, the Soviet Union launched a probe to Venus. Codenamed Venera, the craft beamed back the first images of the planet's surface. Not a tropical paradise, but a hostile desert. Lots of dust and no water. Venus resembles its twin Earth in many ways. Similar in size and composition, they were probably formed from the same cloud of gas over 4 billion years ago. But unlike Earth, 85% of its surface is made up of extinct volcanoes and solidified lava. The clouds are composed of deadly sulfuric acid. Atmospheric pressure is 90 times greater than on Earth, enough to crush a car. But the biggest surprise is temperature. The atmosphere is nearly all carbon dioxide. As on Earth, this gas acts like glass in a greenhouse, admitting light, but trapping heat. On Earth, increasing levels of carbon dioxide are raising temperatures a few degrees. But on Venus, the greenhouse effect has pushed temperatures through the ceiling to levels hot enough to melt lead.
We get there to find out that it's 900 degrees Fahrenheit, and it was very shocking.
The surface is so hot, rocks glow in the dark. Venus would disorient a visitor from Earth. Under permanent cloud cover, you'd lose your bearings. No stars, no sun, no shadows. To find out how these two identical twins, Venus and Earth, grew to be so different, Venus Express carries state-of-the-art instruments designed to unlock the planet's secrets. But the spacecraft's first challenge is just getting there in one piece. 5 months and 250 million miles later, the spacecraft nears Venus, and the most dangerous stage. To achieve orbit will take perfect speed and timing.
Space is never really safe. There's always something that can go wrong, and you have to kind of provide for contingencies for that.
Too fast, and Venus Express will fly off into endless space. Too slow, and the planet's gravitational pull will bring it crashing to the surface.
The actual day of arrival, you have about an hour and a half that it's really kind of tricky. You want to make sure that you hit the right spot relative to Venus and that you're bending around Venus the right way.
To get into orbit, Venus Express must reduce speed by 3,000 miles an hour. April 11th, 2006. The engine fires to slow down the craft. For 10 minutes, Venus Express vanishes behind the planet. If it fails to achieve orbit, it's lost. No second chances. A 4-year mission hangs on hitting the brakes just right.
The most critical maneuver is happening out of sight and out of sound from the Earth. So it's a very harrowing time because you do lose communications for 10 minutes and everybody's on pins and needles to see what happens.
At 9:57 a.m., Venus Express transmits a signal to Earth. The spacecraft's pioneering orbit begins. A multi-million-dollar quest to unlock Venus's secrets. But first, it has to get closer. On an elliptical course around the planet's poles, the craft drops down from 40,000 miles above the surface to just 155 miles. Now, the work begins. The technology on board is a quantum leap forward from the last mission to Venus in 1990. Before, a probe couldn't analyze Venus's surface without landing. All the probes had a short life, crushed by the pressure, melted by the heat, and corroded by the acid. With this mission, scientists have found a way to study the surface without landing and keep their probes safe. Venus Express views the planet using infrared, a wavelength not visible to the human eye. Unlike visible light, the infrared can penetrate areas of cloud that are less dense, allowing the probe to peer through the clouds to the clear atmosphere below. Now, for the first time, scientists can reveal Venus in 3D from the ground up.
With Venus, when you look with the visible eye, you're limited to the very top 1% of the atmosphere. The upper regions, you see these hazes. When you get the ability to look with the infrared light, it allows you to pierce right through all these hazes and see down much lower into the atmosphere. In fact, you can go to the surface.
From 155 miles up, scientists will exploit these infrared windows to map the surface in detail never before seen. Their map will document exactly how Venus and Earth differ. Then, they hope to find out why. Despite decades of exploration, our sister planet can still surprise us. And soon, Venus Express makes a stunning discovery. A spacecraft orbits Venus on a mission to solve a mystery. Venus should be like Earth. But billions of years ago, our twin went its own way and evolved into the burning rock it is today. While studying the outer edge of the atmosphere, Venus Express discovers the first clue to what went wrong. It detects particles escaping into space, mainly helium, hydrogen, and oxygen. Hydrogen and oxygen make water. For years, scientists debated whether Venus's atmosphere held any water. Some argued if early Earth had water, so did Venus. Perhaps enough to form an ocean covering 90% of the planet. Yet Venus Express detects only a small amount of water vapor in the atmosphere. If you condensed all that vapor onto the whole planet, it would create a layer of water barely an inch deep. If Venus once had a vast ocean, what happened to it? Most scientists once thought it simply boiled away. But as Venus Express orbits the planet, scientists are forming a new theory. They believe the culprit is still the sun, but the cause is more than simple evaporation. The sun sustains life on Earth. It also blasts out a constant stream of deadly charged particles. They race out at speeds of up to 1,800,000 miles an hour. It's called the solar wind, and it can devastate unprotected planets. Surrounding Earth is a magnetic field that safeguards our atmosphere. This field is formed by movement in our iron core as the planet spins. But Venus has no magnetic field. Scientists believe it may rotate too slowly to generate one. The rotation is so slow, a day here lasts almost 2/3 of an Earth year. On Earth, one rotation takes 24 hours. On Venus, 243 days.
Well, without a magnetic field like Earth's, Venus is much more vulnerable to being affected by the solar wind and by energy in the upper atmosphere, stripping the atmosphere off into space.
Scientists now believe a combination of evaporation and solar wind strip the planet of its moisture. Venus is closer to the sun than we are, therefore hotter. Its primeval seas evaporated into the atmosphere. That water vapor might still be trapped in the clouds, if not for the solar wind.
The oceans ultimately boil off, and then when you have all that water as vapor in the atmosphere, it's very vulnerable to being broken up by ultraviolet sunlight into hydrogen and oxygen, and then the hydrogen escapes into space, and there you have it. After a few billion years, you've lost your oceans.
The solar wind smashes into the atmosphere, ripping the molecules from the clouds. Over billions of years, the water is lost in space. The oxygen and hydrogen detected in the atmosphere are the last drops of those ancient oceans. Loss of water turned Venus from a warm, wet planet to a burning rock. The atmosphere changed too, from water vapor to carbon dioxide. Ancient volcanoes released trillions of tons of CO2 and set off a chain reaction. A runaway greenhouse effect, leading to global warming gone mad.
The energy for both climate and weather on planets all comes from sunlight. So now imagine that this is sunlight heading towards the surface of a planet. And on a planet like Earth, where there's not much atmosphere, as represented by these atmospheric molecules here in blue, most of the sunlight will miss the atmosphere and just make it to the surface. And occasionally you'll have sunlight scattering off an atmospheric molecule. But for the most part, you just have these yellow rays of sunlight reflecting off the surface. Now, let's set up again and look at what happens on Venus. And I'm putting much more gas in the atmosphere because now we're simulating Venus, which has 100 times as thick an atmosphere. as Earth. Okay, so here's our thick Venusian atmosphere. Here we are back out in space, and let's see what happens to the sunlight in this much thicker atmosphere on Venus. And you'll see maybe a very occasional ray of sunlight hits the surface, but in almost all cases, it gets absorbed in the atmosphere.
The trapped sunlight heats up Venus's atmosphere, and any sunlight that reaches the surface worsens the situation.
So here we are on Venus, our hot surface radiating infrared. And is it making it out into space? Generally, no. Not only is it getting absorbed into the atmosphere, but some of it is bouncing back to the surface. And so on Venus, the infrared radiation is trapped by the thick atmosphere, and the surface and the atmosphere end up heating up.
The process resembles what's happening on Earth, but on Venus, it's out of control. Earth's twin is now the hottest planet in our solar system, even hotter than Mercury, the planet closest to the Sun. Venus is the poster child for climate catastrophe, devastating global warming, and a cosmic hellhole. If Earth were nearer to the Sun, it would look like Venus.
The major difference between Earth and Venus in terms of the evolution of the planets is all about Venus being closer to the Sun. We think that they formed kind of as identical twins, and then it's a different sort of experience of growing up in slightly different neighborhoods closer to the Sun and farther from the Sun that led to this huge divergence we see today.
Life on Earth may be a lucky break, but in the end, we share the same fate.
If you think of the long-term future of the Earth, Earth will go the direction of Venus because the Sun is heating up. And I'm not talking about on a short time scale. If we think about billions of years in the future, really, cosmological timescales, then Earth is destined to end up like Venus.
Scientists long guessed Venus was once like Earth. Venus Express has shown how it evolved into a barren world. More revelations lie beneath the clouds. On the surface, the clouds look calm. But when the spacecraft switches on its infrared thermal imaging spectrometer, its images show how the scene transforms. Violent storms rip across the planet. At the poles, monster cyclones churn the atmosphere. Storm systems that make Earth's worst weather look like a breeze. As scientists study this mysterious planet, they make a startling observation. While Venus rotates slowly, its atmospheric winds travel fast. Venus Express observes winds circling the planet in a mere 4 Earth days. That's 60 times faster than the planet's rotation speed. Scientists call this superrotation. If Earth were like Venus, winds would whip around the planet in just 30 minutes. A speed of 50,000 miles per hour.
When you think about the rotation of the Earth, you've got the rotation rate of the solid planet, 24 hours, and then the atmosphere sort of going along for the ride. But with Venus, it's almost as if the atmosphere doesn't really care what the solid surface is doing. It's got a mind of its own, and is rotating much faster than the solid surface.
On Earth, Wind speed nearly matches rotation speed. So why do Venus's winds travel so much faster than the planet spins? The answer lies in the clouds. On Venus, the cloud layer is up to 12 miles thick. So thick, only a small amount of solar energy reaches the surface. Much of this energy is retained in the upper clouds, 40 miles above the surface. This energy starts the clouds moving at breakneck speeds. Because Venus is closer to the Sun than Earth, the greater the solar energy in its clouds, and the greater the wind speeds. Winds rare on Earth, over 200 miles an hour, are typical on Venus. Venus Express is equipped to solve a riddle found by an earlier mission. A vortex at Venus's North Pole, similar to vortices on Earth. We call them hurricanes. On Earth, they form when warm, moist air from the ocean is heated by the sun and rises to form clouds. As more energy enters the system, the clouds start to spin, creating a hurricane. But Venus has no warm oceans for fuel. So what powers its hurricanes? Venus Express swings down to the southern hemisphere for a closer look. What it finds blows scientists away. A vast hurricane-like vortex, 1,200 miles wide and 13 miles deep, 4 times larger than the largest hurricane on Earth. Not one, but 2 rotating eyes. Scientists believe the cause of the vortices is not only super-fast winds, it's the very motion of the planet.
A huge vortex is caused by all the air flowing in from the equator, and then it has to sink somewhere, which causes this enormous vortex, which is some 2,000 kilometers across.
Wilson believes air from the equator flows to the poles, where it's sucked down to form the vortex. But this air doesn't move in a straight line. The planet's rotation deflects its motion. He suggests this process, called the Coriolis effect, produces the giant vortices.
Let's explain the Coriolis effect using this rotating table. It's the same for a rotating planet. If I let this ball roll across the table, you'll see that it runs in a straight line. And that's because you, the observer, are stationary. You're not rotating with the table. Whereas if, on the other hand, we switch to a camera angle or another observer who's rotating with the planet, this ball will appear to travel in a curved trajectory. So if the observer is rotating with the planet, then it appears that objects experience a force to the right. And this works not only for balls, but also for parcels of air in the atmosphere. If the air at Venus is heated at the equator and moves towards the poles, it's then bent towards the right if it's in the southern hemisphere, or towards the left if it's in the northern hemisphere.
As the winds move toward the poles, the Coriolis effect makes them spin, which creates the vortex. Wilson's theory seems logical. Vortices also occur at Earth's poles. But while Earth's polar vortex is relatively stable, the double-eyed monster on Venus is an ever-shifting whirlwind. To find out what makes the vortex so chaotic, recreate it. Wilson uses water to simulate Venus's atmosphere.
We've got the rotating atmosphere simulated by the rotating tank, and then we've got this thin ring here which spins at a different speed, faster than the rest of the atmosphere. And what we find is that the flow in this region is unstable, it sort of oscillates in and out. And we think that's quite representative of what happens around the edges of the polar vortex on Venus.
When Wilson adds dye, his simulation reveals the shifting shapes at the edge of the vortex. These chaotic winds show the power of Venus's atmosphere. But vortices aren't the only bizarre weather. On June 9th, 2006, Venus Express discovers an eerie phenomenon. The spacecraft detects an intermittent disturbance that sounds like a whistle. A brief, low-frequency electromagnetic burst. This is the actual recording. To anyone else, baffling. But to the mission team, a revelation. The signature of lightning. UCLA's Professor Christopher Russell has long believed lightning occurs on Venus. The spacecraft's discovery presents a riddle. On Earth, water drives thunderstorms. Warm, moist air collides with cold air. Water droplets and ice crystals rub together, creating positive and negative charges. The electrical buildup discharges as lightning. Venus's atmosphere has little water. Most of it has been stripped away by the solar wind. So what else could produce lightning? Thanks to data from Venus Express, a controversial theory gathers new weight. Russell's candidate for the cause of lightning? Clouds of sulfuric acid. On Earth, sulfuric acid clouds form when sulfur dioxide is released from volcanoes and mixes with water vapor. The same thing happens on Venus. 2 decades ago, Project Magellan, the first spacecraft to map Venus, discovered widespread evidence of a volcanic past. Over eons, volcanoes release trillions of tons of sulfur dioxide. Some remained as a gas. The rest mixed with water vapor to form sulfuric acid clouds. The speeding winds energize these acid clouds and create ideal conditions for lightning.
We think now that it's sulfuric acid clouds and Venus's winds, and the winds can then provide the energy source in the cloud for the charge separation.
Sulfuric acid does on Venus what water does on Earth. Acid drops rub together and create positive and negative charges.
I was looking for lightning and looking for the proof that it really existed, and to find it is like a personal victory.
The discovery of lightning is electrifying. Lightning is an ingredient of life. An even greater shock was in store. The hellish planet might not be dead. Eons ago, Venus's volcanoes spewed out vast clouds of sulfur. But today, tests show the level of sulfur is fluctuating. Since volcanoes discharge lots of sulfur only when they erupt, the fluctuations mean one thing. The volcanoes on Venus must still be active. Scientists have found active volcanoes in only a few places besides Earth. In 2007, the New Horizons probe captured an eruption on Io, one of Jupiter's moons. To find active volcanoes in the inner solar system is big news. It means Venus may not be a dead rock, but a living planet. Venus Express takes a closer look. The probe exploits the infrared windows to peer through the clouds. Below, mountains and valleys, smooth plains, impact craters, and flat-top features like pancakes, all made of lava. 85% of Venus's surface is paved with lava. Why so much puzzled scientists. To understand Venus's vast lava fields, scientists look to its calmer twin. Earth's crust is made up of interlocking tectonic plates that drift over its liquid mantle. Most of our planet's volcanic activity is found where these plates move together or pull apart, allowing heat from the core to escape. No mission has ever found evidence of plate tectonics on Venus. Its crust is solid. Without plate tectonics to cool Venus, scientists suggest heat from the core built till it couldn't be contained. Then virtually the whole planet erupted, releasing so much lava, it recycled the crust and resurfaced the planet.
This is a demonstration of the Venus resurfacing. We're going to demonstrate with some pudding in a pan over a hot plate. And this heat from the hot plate represents radioactive heat from the inside of Venus. And here we're seeing the first signs of the interior heating the crust on the surface. And that crust is stagnant. It's not moving, it's keeping the heat inside. And perhaps at this moment the surface might even crack in some places, and the molten material, the molten rock under the crust would erupt and flow out onto the surface, covering up all the craters and all the mountains. And at this point, we can see several small volcanic eruptions along those fissures.
Scientists date the resurfacing to 500 million years ago. A slow process that took tens of millions of years. This cataclysmic series of eruptions released trillions of tons of sulfur dioxide and carbon dioxide, replenishing what the solar wind removed. Yet surveys of Venus reveal not all the planet was resurfaced. Rocks in the highlands are much older than the lava covering most of the planet. They offer a clue to conditions in the distant past. Kevin Baines discovered these rocks weren't born on dry land.
On Venus, most of the rocks are basalts. They're made out of volcanoes spewing out their lava. But we have found a very interesting result in the last few months. That is, the highlands are special. On the highlands, the tall mountains of Venus, we're finding evidence of rocks that were created in the presence of water, as if billions of years ago they were formed perhaps in an ocean, and then geologic processes have risen them up since then.
The rocks provide hard proof that Venus once had oceans, which raises a provocative question. On Earth, life began in the oceans. The other ingredient to kickstart life is lightning. And lightning occurs on Venus. If Venus had water and lightning, Did it once have life? Scientists have plenty of proof that Venus and Earth were once twins, and that Venus had two of the ingredients of life: water and lightning.
Lightning is important because it's something that produces exotic species. For example, nitrogen and oxygen combined to produce nitrogen oxides, which are important for life and important for producing chemicals that can't be produced any other way in a planetary environment.
With water and the means to kickstart evolution, perhaps Venus once had life, and maybe still does. The first clues arrive from Venus Express. 155 miles above the surface, a camera is switched to ultraviolet. Unlike infrared, the shorter wavelength of UV is scattered by Venus's cloud layer, enabling the scientists to explore the upper regions of the atmosphere. Their images reveal intriguing dark markings where more UV is being absorbed. This shows that something besides sulfuric acid is trapping sunlight. The mission team calls the dark areas absorption patches.
There's been great interest in the ultraviolet absorbers on Venus. They absorb about half of the sunlight that's hitting the planet. They're in the clouds of Venus, and it's been suggested that they might be associated with life forms.
Life forms, like microbes, living in hurricane-force winds and sulfuric acid clouds, using UV light in some weird photosynthesis. But what kind of life could survive such conditions? Biologist Lynn Rothschild studies organisms that live in extreme environments. She has discovered microbes called extremophiles thriving in some of the harshest conditions on Earth, like Yellowstone National Park. With the highest concentration of thermal springs in the world, it opens a window into how life might survive on Venus.
What you see behind me is really ground zero for where people started to understand organisms that could live in extremely acidic conditions. Before that, people thought conditions like lemon juice would be totally outside the realm of where a living organism could be.
These geysers, powered by volcanoes, mimic conditions on Venus: hot and acidic.
This stream is just phenomenal. It's about pH 3, it's about 40 degrees centigrade. A little hotter than warm to the touch. Actually, it's fairly warm to the touch. What you see in here is almost a pure culture of some red algae. I know it looks green, but they are actually red algae that don't have a red pigment.
Extremophiles like these can survive in battery acid and temperatures above boiling point. These organisms have evolved to survive not only the heat and the acid, but levels of other chemicals that would kill most life.
These particular organisms, Cyanidium, are really neat because not only do they live at low pH and in warm temperatures, and they photosynthesize, but they've been shown to be able to survive in pure CO2, pure carbon dioxide. Even Venus doesn't have as high a carbon dioxide level as that.
The organisms show life can survive hot, acidic, carbon dioxide-rich environments, like Venus. If life can survive in Yellowstone, why not on Venus? Scientists believe the surface itself is too savage. Temperatures reach 900 degrees, and the pressure is bone-crushing. But not in the clouds. 30 miles up, temperatures reach only 176 degrees, much closer to the kind of heat microbes endure on Earth. Could life have begun in Venus's ancient oceans? When the water evaporated, the microbes may have gone with it. Here, in the cooler acidic clouds, they could survive. But how can life exist without water?
There is water vapor up in the clouds in Venus, and we have some indication that organisms on the Earth, for example lichens, can use water vapor as their source of water. So that's pretty encouraging for life in the clouds, at least in terms of having water available.
To see if life exists in moist, acidic clouds, Rothschild collects air samples above a hot spring. The acidic steam mimics the clouds of Venus.
I can see a little green on the mouth here. That's encouraging. Maybe there really is something in there.
Analysis shows microbes can exist in hot acidic steam, suggesting life may survive in Venus's clouds. To further test the theory, Lynn sends organisms high into the atmosphere. She's launched a whole spectrum of microbes. Some to over 100,000 feet. A zone where temperature and pressure drop so low, most life would die.
Okay. Now let's hope we put enough in it.
Many of her subjects survived. Some researchers have even found organisms that can reproduce high up in the atmosphere.
The clouds on Venus are continuous and long-lived, so you could imagine creatures that live in the clouds and reproduce in the clouds and even seed other cloud particles, and they're not going to last forever because they're going to fall out, but as long as they last long enough to reproduce themselves, then you could have a self-sustaining colony of life in the clouds.
Research shows life in hot, acidic clouds is theoretically possible. Perhaps microbes live in the clouds of Venus, hidden in those strange dark patches. Venus Express has traveled 87 million miles around the planet and completed 100 weeks of collecting data. It proved that Venus once looked like Earth. A habitable climate, vast oceans, perhaps even life. But too near the sun, Venus was doomed. Earth blossomed, Venus burned. Yet even here, life may thrive. Maybe tucked in blankets of clouds. We may have to wait years for the secret to be revealed. But someday, another mission to Venus may find the holy grail of space. Life beyond our world.
Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
Snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as drop stones. The drop stones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these drop stones at the Flinders Range.
This is an example of a drop stone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These drop stones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the drop stones on the ocean floor.
These drop stones are evidence that at some point, this area was covered in a thick layer of ice. But it's difficult to explain how ice could have covered the sun-baked mountains of southern Australia. Unless the continent itself was in a very different place. The continents haven't always been where they are now. They move very slowly across the Earth due to the movement of tectonic plates. 650 million years ago, around the time the Flinders drop stones landed here, the continents were positioned very differently. Since the drop stones formed under ice, perhaps Australia sat nearer to the poles where temperatures were lower. To locate the position of a continent in the distant past, scientists study the magnetic identity of rocks. Certain sedimentary rocks contain magnetic particles. When the rocks form, these iron particles line up with the Earth's magnetic field. Near the poles, they align at right angles to the sedimentary layers. And around the equator, they align parallel to the layers. Even if the rock moves, the distinctive configuration of these magnetic particles remains the same, and provides a kind of geological fingerprint of the rock. Professor Joe Kirschvink at Caltech Pasadena is fascinated by magnetism.
Magnetism is magic. I've even named my eldest child after a magnet, so I enjoy magnetism.
Kirschvink and his team analyzed the 650-million-year-old rock surrounding the dropstones. The results were unexpected.
That part of Australia was within 5 degrees of the equator, and it just was the most weird place to expect a glacier.
But Kirschvink had to be sure that this ancient rock still held its original magnetic signature. If the rock heated up after it formed, its native magnetism would have changed. Back at Flinders Range, Kirschvink's team uncovered clearly striped sedimentary rock that provided proof.
Here, tens of thousands of layers of mud grew one at a time, upward and upward, in a glacial lake at the edge of a 635-million-year-old ice sheet.
When this rock formed, layers of sediment built up in distinctive horizontal lines. By comparing the direction of the layers of sediment with the direction of the lines of magnetism, Kirschvink could determine whether the rock's magnetic signature had changed.
We can explain the process of magnetism with a simple eraser. If the rocks formed on the equator and gained their magnetism very early, we would expect the magnetic direction to be parallel to the bedding very precisely like this. And then, since the rocks are soft, if they get squeezed or deformed geologically, you would expect them to rotate like this, and the magnetism would shift with the bedding. On the other hand, if the rock had been squeezed and deformed first, and then gained the line of magnetism like this, we would see them warped relative to the bedding today.
If the rock still had its original magnetic orientation, the lines of magnetism would follow the lines of sediment. But if its orientation had changed, the magnetism would cut through the sedimentary layers. Raub drills into the formation to retrieve solid cores of the rhythmic rocks. Back in the lab, the team analyzes samples of rock using a custom-built hypersensitive magnetometer. This magnetometer measures the orientation of the magnetic particles in the rock. It confirms that the particles were aligned with the rock layers. Kirschvink was astonished.
Quite frankly, when I saw the original study, I didn't believe it. And what in fact we see is that they're like this, and as the rock was warped, magnetism warped. That proves conclusively the magnetism formed before the rock was solidified.
This discovery seems to provide irrefutable evidence that the glacial rocks formed close to the equator. Paul Hoffman, professor of geology at Harvard University, was intrigued.
So if there were glaciers close to the equator, where the temperature was warmest, one has to assume that there was also ice in higher latitudes where the temperatures were colder.
650 million years ago, Australia sat near the equator. And yet evidence suggests that its arid rocks lay buried beneath ice. And if there was ice at the equator, there would have been ice all over the globe. These dropstones became the catalyst for a radical theory: Snowball Earth. This is a theory about the most extreme ice age imaginable. And if it happened before, it could happen again. Our world has been through many periods of extreme climate change. But some scientists have proposed that 650 million years ago, the Earth may have frozen over completely. This radical hypothesis raises one crucial question. How could it have happened? Kirschvink proposes that the giant freeze was triggered by the same mechanism that lies behind today's global warming, the greenhouse effect. Except 650 million years ago, it worked in reverse. Greenhouse gases in our atmosphere act like an insulating blanket, trapping the sun's energy to keep Earth's temperatures mild. When the snowball began, scientists suspect that levels of these vital gases fell dramatically.
The Earth's atmosphere might have been filled with methane and carbon dioxide, and the Earth became addicted to this high-level carbon dioxide and methane in order to keep its temperature. Then, if some unknown event crashed the carbon dioxide out of the atmosphere, Earth might have run away into a Snowball Earth.
If enough carbon dioxide had been pulled out of the atmosphere, an anti-greenhouse effect would have plunged the Earth into a deep freeze. But this theory is only possible if there's a mechanism that could pull all the CO2 out of the air. In fact, carbon dioxide is removed all the time through a process called silicate weathering.
Weathering is a geological term for the decomposition of rocks under the influence of the weather. It's a process that converts solid rock into soil. Now, its importance for the climate is that weathering consumes carbon dioxide, which is a major greenhouse gas in the atmosphere.
Carbon dioxide reacts with water vapor in the atmosphere to form carbonic acid rain. This acidic rain weathers limestone on land and carries away the eroded sediment to the sea. Here it builds up, eventually forming limestone on the sea floor.
So the presence of the limestone is the evidence that weathering is occurring.
The more carbon dioxide gets locked away in limestone, the cooler the Earth becomes. But if this is happening all the time, something must have amplified the process for the whole world to have frozen over. Again, clues lie in the position of the continents. The movement of tectonic plates continually shifts the continents around the globe. Today, a lot of the continents are located in higher latitudes. If the Earth cools, the continents near the poles ice over. The ice prevents the rocks beneath from being weathered by carbonic acid rain. This means that the weathering cycle is kept in balance. With less carbon dioxide locked away in limestone rock and more in the atmosphere, the planet warms. Scientists have worked out that 650 million years ago, the continents were clustered around the equator, where it's warm and wet. Consequently, the global rate of weathering would have been higher.
During the Snowball Earth, we suspect that there were many more continents at the equator, and this would actually lead to a situation that would make the planet vulnerable to a global glaciation.
As the Earth cooled, ice formed at the poles. But because there were no continents in the higher latitudes, ice accumulated on sea rather than on land. There was nothing to regulate the weathering. The cooling continued unchecked, and the world got colder and colder. This runaway scenario is certainly plausible. But although extreme weathering could be behind an ice age, it doesn't explain how the Earth could have iced over completely. Geologist Galen Halverson from Adelaide University studies triggers of the snowball.
One of the hardest parts about understanding the snowball is really how it began. We think that it must have began like a normal glaciation.
Normally, living things help to regulate the Earth's climate by maintaining the delicate balance of carbon dioxide. Plants consume carbon dioxide. Animals produce it. These consumers and producers help to regulate the climate, ensuring the Earth is neither too hot nor too cold. If there's more carbon dioxide in the atmosphere, it gets warmer. This causes plants to grow faster which in turn draws out more CO2 from the air.
So that is a feedback against it getting too warm. And in reverse, if it starts getting too cold, then the biosphere responds by not drawing down as much CO2, and that allows CO2 to go back up. So there's a sort of buffer in the form of life on Earth that prevents temperatures from getting too cold or from getting too hot.
But rewind 650 million years and witness a very different story. Life on land was in its early stages of evolution. Most living things were in the oceans. This half-formed biosphere could not prevent the Earth from swinging to wild extremes of temperature. Colonies of single-celled organisms called cyanobacteria were the first to photosynthesize. They pulled carbon dioxide from the surrounding water to precipitate calcium carbonate, and they used this to make dome-like structures of rock. Geologist Jim Gehling is an expert on these early life forms.
Temperatures were dropping at this time, 650 million years ago, for the very good reason that carbon dioxide, the principal greenhouse gas, was being taken out of the atmosphere and locked away on the seafloor.
This trapped carbon dioxide can still be seen today in stromatolite reefs.
This is actually solid carbon dioxide, and I can release that carbon dioxide after all those hundreds of millions of years when I put this weak acid on the rock. And there you see it erupt as the white bubbles of carbon dioxide spring out of the rock, go back into the atmosphere to take up their role all over again as greenhouse gases.
The more carbon dioxide the cyanobacteria locked away, the cooler Earth became. Our planet was hurtling towards a deep freeze that would last for millions of years. $650 million years ago, the Earth's temperature plummeted. Huge sheets of ice spread across the planet. Eventually, they engulfed most of the land and sea. This was no regular ice age. Ice ages are nothing out of the ordinary. We experience them every 100,000 years or so. They are mainly caused by small changes in the Earth's orbit, which alter its position relative to the Sun. When our planet receives less of the Sun's energy over a number of years, ice forms high in the northern hemisphere and advances down. At the height of the last ice age 21,000 years ago, these icy sheets reached down as far as New York. But the tropics stayed warm. Only about 30% of our planet froze. But 650 million years ago, some scientists believe the ice kept coming, until eventually, most of the globe was covered. What could have caused this runaway cooling? The answer must lie in how our planet keeps or loses the sun's energy. The Earth's surface is made up of land, open ocean, and ice. These all reflect sunlight to a different degree. The amount of light a surface reflects is known as its albedo. Deep dark ocean has a low albedo, since it absorbs a lot of sunlight. White snow and ice have a very high albedo, since they reflect more of the sun's energy back into space. Tim Raub demonstrates how dark and light colors heat up under the sun.
The temperature of a white car sitting in the sun is only 120 degrees. The temperature of a black car sitting in the sun is 144 degrees. The black car absorbed light, the white car reflected it.
White reflects more sunlight, keeping whatever it's covering cooler. The more ice that covers the Earth, the more of the sun's energy reflects back into space, and the colder the planet becomes. This cooling leads to more ice forming, which further increases the surface albedo. This is known as ice albedo feedback. And something may have accelerated this cycle of cooling even more. New research suggests that when seawater freezes at very low temperatures, its composition changes and it can become more reflective. At the University of Washington's Polar Science Center, Bonnie Light studies the relationship between ice and light. In the cold room, she freezes buckets of salt water at different temperatures. One of the buckets is exposed to Snowball Earth temperatures of -10 degrees. The surface of this ice becomes much whiter.
Okay, so this bucket contains seawater that was frozen in a cold room at 5 degrees above 0 Fahrenheit. And we consider this a good laboratory analog for modern day sea ice on planet Earth. And you can see that the surface of it is kind of gray colored, dull appearance. And this bucket also has salt water in it, although this salt water was frozen at about 10 degrees below 0 Fahrenheit. And we consider the ice in this bucket to be a good analog for sea ice on Snowball Earth because it's very cold.
At Snowball Earth temperatures, the composition of sea ice changes, turning its surface from gray to bright white.
And you can see that these crystals in this case have started to collect at the surface of this cold ice. And so I can kind of scratch away these crystals, and you can see that this is basically just a deposit on the surface of this cold ice.
At -10 degrees, salt molecules in the ice begin to form tiny crystals.
If you can isolate them under the microscope, they look like little gemstones. They're really quite beautiful.
These bright crystals have a dramatic effect on albedo. The white surface scatters more of the sun's energy and reflects it back to the atmosphere, causing temperatures to drop even further. In the 1960s, Soviet climate modeler Mikhail Budiko demonstrated how runaway ice albedo could cause a cooling Earth to freeze completely. Like many of his contemporaries, Budiko was worried about the effects of a nuclear winter. Nuclear explosions create clouds of smoke and dust, which block the sun's energy and lower the Earth's temperature. Budiko developed a mathematical model to work out the odds of a global ice age. He showed that if the Earth's climate cooled enough for ice to form in the lower latitudes, then the ice albedo would rise at a faster rate. And once the glaciers reached a certain latitude, the Earth would tip into a snowball-like state.
Somehow or the other, the ice line, the glaciers, reach some critical latitude, around 30 degrees. And once they hit that latitude, very, very rapidly, the Earth would have been entombed in ice.
Budiko's groundbreaking work showed how this snowballing effect could create a totally frozen planet within just a few decades.
Budiko's work was extremely important in demonstrating that it was possible that Earth might slip into a climate catastrophe which was covered completely with ice. It had not been recognized as a possibility before that.
If the Earth became entirely covered in ice, nearly all the heat it received from the sun would be reflected back into space. The planet would become locked in ice. So if runaway freezing trapped the Earth in ice, how did it ever escape? Some scientists suggest that 650 million years ago, our entire planet was locked in an extreme ice age. It was a unique event, the result of a set of improbable triggers. Or so they thought. Then, in 1997, evidence emerged that it could have happened more than once. It came from glacial deposits in South Africa that were over 2 billion years old. Paleomagnetic evidence suggests that these formed near to the equator. Geologist Paul Hoffman believes this could be proof that the Earth froze over completely at least twice in its history.
The best evidence for a snowball Earth 2.22 billion years ago is paleomagnetic evidence from South Africa. there are glacial tills there, boulder clays, that formed very close to the equator.
This discovery raised the possibility that the snowball wasn't a single event, but a recurring condition. Scientists raced to find the trigger for this earlier deep freeze. The cooling appeared to coincide with the Great Oxidation Event. Deep in the ocean, some of the oldest organisms on Earth evolved a mechanism called photosynthesis. The ability to convert carbon dioxide into oxygen using the sun's energy. As these photosynthesizing microbes thrived, they had a profound effect on the Earth's climate. 2 billion years ago, our sun was weaker. Our planet relied on greenhouse gases like carbon dioxide and methane to maintain its temperate climate. But photosynthesis uses up carbon dioxide. It also produces oxygen, which destroys methane. The result, a double whammy. Levels of both these vital greenhouse gases plummeted.
You have a precarious situation. You have a planet that's greenhouse needs methane, and you suddenly evolve a bug that destroys the methane.
Maybe the first bacteria that photosynthesized crashed the carbon dioxide and methane from the atmosphere and triggered the first Snowball Earth.
As oxygen production soared, methane levels tumbled. With the loss of that greenhouse gas, the Earth spiraled into a deep freeze.
It's kind of a frightening conclusion that a single-celled mutant bug destroyed an entire planetary ecosystem. Destroyed it. Turned it into a snowball for maybe 35 to 100 million years.
Some scientists now think that our planet has been encased in ice on at least 3 separate occasions, and each time under different circumstances. But these Snowball Earth scenarios present a huge problem. If our planet was trapped in ice, how did it ever escape? Something must have caused a global meltdown. Evidence of the thaw is right here. On top of the dropstones sit layers of a peculiar reddish-gray rock. These layers stretch for miles in the Flinders Range, Death Valley, and almost everywhere where the glacial rocks appear. These are carbonate rocks, which form in warm, shallow seas. But here, they appear right on top of the glacial deposits.
So here's a sample that actually shows the end of the snowball event. So that's an ice-rafted stone dropped out of an iceberg. And these are little grains that also fell out of an iceberg. And immediately on top of that, without any break in sedimentation, is cap carbonate that's precipitating directly out of the ocean and accumulating on the seafloor. And exactly the same relationship is seen all over the world.
Their presence is evidence of a sudden and drastic temperature increase. Only one thing could have triggered this: a huge injection of greenhouse gases such as carbon dioxide. In order to melt Snowball Earth, concentrations of carbon dioxide had to be around 350 times higher than they are today. But if the whole planet was encased in a thick layer of ice, where did the carbon dioxide come from? Caltech professor Joe Kirschvink had a revelation.
I woke up in the middle of the night and said, that's gotta be it. It just dawned on me that these subaerial volcanoes, like in the Aleutians and the Yellowstone, these volcanoes sit and they spew CO2 into the air.
Even beneath the ice, volcanoes would have continued to release immense volumes of carbon dioxide. With the rest of the planet still ice-locked, there would have been no mechanism to remove it from the atmosphere. Over millions of years, levels of this greenhouse gas would have built up, eventually producing enough warming to offset the ice albedo. The ice melted, sending global temperatures spiraling upwards. As this melted ice water evaporated, it swelled the atmosphere with moisture, creating torrential rainfall. Carbon dioxide in the atmosphere acidified the rain. Acidic downpours rapidly eroded limestone, washing sediment down into the oceans. Here, layers of carbonate sediment accumulated on the sea floor to become carbonate rock. Dan Schrag demonstrates what could have happened.
Instead of carbonic acid from carbon dioxide, we're going to use a little stronger acid to make it go a little faster. This is nitric acid, and when we add it to the limestone, it will dissolve away the limestone and ultimately create a very clear solution. So you can see it bubbling away. And when this is added to the ocean, it reacts and creates the cap carbonates that blanket the top of the glacial deposits.
But still, not everybody is convinced that the planet was ever entirely covered in ice. Some scientists argue that the chances of life surviving a full-on snowball are virtually nil. Above the ice, the freezing conditions were too hostile, while below it, life was cut off from sunlight. Yet there is evidence that photosynthesizing organisms did survive the freeze. Single-celled cyanobacteria existed right the way through. Cyanobacteria can survive extremes of temperatures many degrees above and below zero. But if the oceans froze over, a thick layer of ice would have sealed them away from the sunlight. With their energy source blocked, they would have died out.
If you'd been diving on a tropical reef before Snowball, this is what you would have seen. Slime world, mounds of slime on the sea floor. And if you touch them, you'd find out that they're actually rock. A surface covered with slimy material, which is actually cyanobacteria, the earliest, the most primitive form of life that's been around for 3 billion years up until this point and is still around today.
Critics argue that nothing could have survived the ferocious conditions of a total global freeze. They maintain Snowball Earth was nothing more than a severe ice age with extensive glaciers and a belt of open water around the equator. Philip Allen, a geologist at Imperial College London, believes that the evidence for a frozen planet is flawed.
I am not in agreement with this Snowball Earth hypothesis. The major hole in the theory, as far as I'm concerned, is that the sedimentary rocks deposited during the glacial periods do not support the idea of a long-term global freeze.
Philip Allen's counter-evidence includes the ripple-like patterns in rocks formed 650 million years ago.
When you look at those sedimentary rocks, it indicates open water. The wind was able to blow over the water surface and form ripples, wave ripples on the seabed. So they are really conclusive proof of an open water surface rather than an ice-covered one.
Waves in an open sea left imprints in the sediment of the sea floor. When the water disappeared and the sediment turned into rock, the ripples remained. Allen and others propose an alternative to the Snowball Earth. It's known as the slush ball. In their version of events, the Earth never froze completely. Some patches of open land and sea remained. But proponents of the snowball theory don't suggest that the frozen planet was without any open water. Schrag believes that life could have survived in ice holes around sources of geothermal energy.
Even in a completely ice-covered planet, there's still plenty of places where there are hot springs, geothermal heat from volcanoes, probably thousands and thousands of such little holes. And in many of those little holes, you could sustain life throughout the Snowball Earth period.
The reality is, we may never know if the world was ever completely frozen over.
Sometimes people think of the Snowball Earth like a cartoon, an oversimplified planet, but the real world is much more complicated than that.
Whether slush ball or snowball, everyone agrees there was a profound global freeze. And when our world emerged 635 million years ago, something unexpected appeared. Life. Far more complex than anything that had gone before. After the big freeze, life on Earth exploded. Our planet, 650 million years ago. Temperatures plummeted, turning our planet into a hostile place. Yet somehow, life survived. And as soon as the frozen Earth began to thaw, it blossomed. And there was an unprecedented explosion of life on Earth. Before the deep freeze, life was primitive. Single-celled organisms and algae were mostly confined to the oceans. Shortly after it ended, the first multicellular animals appeared. The big question is, did the global cooling trigger this great leap in evolution?
Well, the best evidence is the coincidence in timing, the fact that the first fossils of multicellular animals occur less than 3 million years after the last snowball termination.
Shu-Hai Xiao is a geologist at Virginia Tech. He unearthed some of the oldest multicellular animal fossils in the world in a mine in southern China.
The fossils are really small. They're about half millimeter in diameter, so you can barely see them with naked eyes.
Under a microscope, he discovers that the fossils are very primitive animal embryos. Some fossils show clusters of 2, 4, 8, and more cells.
It was really exciting when we found those. Those are some of the earliest animal fossils, and they have found in rocks that were deposited almost immediately after the Snowball Earth ended.
Fossils of these animal embryos date back to just 3 million years after the global freeze ended. That might seem a long time in human terms, but geologically, it's the blink of an eye. Over the next 80 million years, animal life exploded. In the Flinders Ranges in southern Australia, geologists have found some of the oldest fossil evidence of complex multicellular life. These creatures bear little resemblance to life today, but they offer clues to the genesis of early life. 650 million years ago, this area was beneath a shallow sea. Bizarre, soft-bodied organisms similar to jellyfish or flatworms lived on the sea floor. Some of the organisms got trapped in fine silt of tidal flows where they fossilized. Jim Gehling has been investigating these early animals.
Probably our ancestors lie in these rocks. This thing here, Dickinsonia, can best be described as some kind of a pancake or mat-like worm creature. It doesn't have a proper head, it has what appears to be a gut, very fine segments.
But this doesn't explain how the severe planetary freeze could have triggered a leap in evolution. What we do know is that there is a striking coincidence between the rise of oxygen and the end of the snowball. Oxygen levels rise following these global ice ages because of a chemical reaction between ice and sunlight. 650 million years ago, there was no ozone to stop the sun's ultraviolet light hitting the Earth's icy surface. This UV light reacted with water vapor to form hydrogen peroxide. The hydrogen peroxide remained in the ice for millions of years. But when the ice melted, the hydrogen escaped, and the peroxide converted into water and oxygen. Oxygen reached the same level as we have today. At roughly the same time, the first complex animals appeared. More oxygen enabled life to become multicellular. A single cell can take up gases and oxygen from water. oxygen fuses across the cell membrane into the cell. However, when several cells link together, it's harder for oxygen to diffuse from one cell to the next. The pressure of oxygen needs to be higher.
You need to have a high enough pressure of oxygen to have a circulatory system bring the oxygen all around the body. After the last Snowball Earth, oxygen seems finally to have been high enough to support hundreds, thousands, millions of small early animals on the seafloor.
Oxygen turned out to be the linchpin of evolution. The ability to use oxygen enabled life to become dramatically more diverse.
Oxygen gives us 20 times more energy, or more than 20 times more energy, than any other thing that we can breathe, or that life can breathe. You can have bigger animals, you can have more active organisms, you can have plants that grow and transport liquids from roots to the leaves, and you can have birds energetic enough to fly. Without oxygen, we would all be slime.
A frozen Earth may have given early life a push forward. But if the world were to freeze over again, we'd struggle to survive. We know it's happened several times before. The question is, could it happen again? One factor in our favor is the sun. Over the last 4.8 billion years, it has been getting more and more active as nuclear fusion generates more and more heat. The sun today is about 6% warmer than 650 million years ago. So in the short term, another deep freeze is unlikely.
The sun is warmer today. That probably helps us out. But until scientists really understand what causes Snowball Earths, I don't think any of us know whether we're in danger or not of a recurrence.
But there is one possibility that could result in another global freeze: a shift in the position of the continents. We know their arrangement influences the climate. If the majority of the continents were clustered on or near the equator, the Earth would be more likely to turn into a snowball. Cooling temperatures would cause ice to form in the open ocean of the poles, while weathering would continue on the continents. With more and more carbon locked away, temperatures would plummet.
If all the continents were near the equator, then the Earth could get colder and colder, and sea ice could form and get to lower and lower latitudes, closer and closer to the equator.
Today, our world seems safe. Most of the continents are near the poles. But plate movement never stops. At some point, millions of years in the future, the continents may group around the equator once again.
I think it's possible someday, if the continents were in a very different position, maybe hundreds of millions of years from now, that we could indeed have another Snowball Earth.
It's unlikely that mankind will be around to witness another Snowball Earth. But the Earth will still be here. And just like it has in the past, our planet will survive and enter a new phase in its extraordinary history. 65 million years ago, a 1,000 billion ton asteroid smashes into the Earth, wiping out the dinosaurs. Massive impact events are likely to happen once every 75 million years. Today, scientists scan the skies for these giant killers. But an asteroid just 150 feet across could devastate a city the size of New York. Asteroids this size could hit any time. And right now, there is nothing we can do to stop them. It's a nightmare scenario. 1,000 billion tons of rock on a collision course with Earth, hurtling towards it at over 50,000 miles per hour. It hits with the force of 300 million nuclear weapons. Enough energy to wipe out every human being on the planet. This is no nightmare. It's real. 65 million years ago, a rock this size smashes into the Earth. And wipes dinosaurs from the face of the planet. It could be 10 million years before the next impact this big. But smaller asteroid impacts can also be devastating, and they happen far more often. Around 50,000 years ago, an asteroid slams into the Arizona desert, hurling 175 million tons of rock into the air. Meteor Crater is nearly a mile wide and 570 feet deep. Amazingly, the Canyon Diablo asteroid that created it was only 130 feet in diameter, about the size of a small jet plane. There are more small asteroids like this in space than large ones, and they can hit the Earth as often as every few hundred years. One scientist at Northern Arizona University thinks Meteor Crater has a message. Professor Ted Bunch.
Events like this, smaller events, they could happen anytime.
And they're capable of massive destruction. The extreme heat of this blast tore through the desert sandstone.
This is coconino sandstone, and it's in pretty good shape. And there's a piece here. This is also coconino sandstone that is severely shocked. Probably temperatures exceeding maybe 3,000 degrees Fahrenheit. Huge amount of pressures, and you can see the difference. This used to be this.
Imagine the same thing happening today. What would a 130-foot wide object like this do to New York City?
If this meteorite had hit Manhattan yesterday, about 80% of the people would have had serious injury or died. All the boroughs of New York would have been affected, either by the heat, the shock wave, the seismic activity, crumbling of buildings, and collapse.
Everything within a 5-mile radius would be obliterated. Asteroids have crashed into our planet ever since its formation. The key to their destructive powers lies in their mass and the speed of impact. As an asteroid hurtles towards Earth, it builds up huge amounts of kinetic energy, much like this speeding car. The faster the car goes, the greater the kinetic energy, even though the car's mass stays the same. When the speeding car hits a brick wall, it doesn't inertly stop. All the kinetic energy is converted into an explosive force. The crash generates heat, metal bends, plastic and glass shatter. An asteroid behaves exactly the same way when it impacts the Earth, only because it's traveling at 50,000 miles per hour, the explosion is far greater. Here in Arizona, evidence of the impact stretches 6 miles from the crater's edge. Pulverized rock particles called impactites shot across the landscape at deadly speeds.
We have impactites, all these little dark guys. Those are melt rocks. There's literally tens of thousands of them right in this particular area. These were ejected as far as 3 to 5 miles under very high velocities, 2 or 3 times the speed of a rifle bullet. But if you were an animal in this area and you had thousands of these particles coming at you, you'd be toast.
Impactites are a major clue to an asteroid strike and can reveal previously unknown impacts. Fossil hunters in Alaska uncover fragments of tusk from woolly mammoths. They are peppered with buckshot-like particles and date back 34,000 years to a time when the number of large mammals in the region inexplicably dropped. Have fossil hunters uncovered evidence of an undocumented asteroid impact? Dr. Richard Firestone searches for evidence.
We analyzed several of the particles from various tusks, and they had the unique signatures of meteorites. They were rich in iron and nickel, which is a critical component of most meteorites.
This is strong evidence that these woolly mammoths died from an asteroid impact. The force of blast was devastating.
We did an experiment with a shotgun to see what would happen if you shot a mammoth tusk, and they simply bounce off the outside. Nowhere near enough energy for that.
A shotgun fires at 600 miles an hour. Asteroid fragments travel over 30,000 times faster.
In order for the impact particles to penetrate the tusks as they did, they'd have to have been moving at tens of miles per second.
Firestone's mammoth died in an asteroid impact 34,000 years ago. The impactites embedded in the mammoth tusks prove that previously unknown asteroids have struck the Earth. And new evidence reveals that they didn't just kill mammoths. Humans died too. 13,000 years ago, North America is locked in an ice age. Large mammals like giant sloths and woolly mammoths roam the land. The nomadic Clovis people live alongside them. Then the fossil record stops. Many species of mega mammal abruptly disappear. What causes this sudden, mysterious disappearance? The Clovis culture also vanishes from the archaeological record. Is it starvation? Disease? No one knows for sure. Now a cave in northern Ohio may hold the answer. 30 feet underground, an archaeologist from the University of Cincinnati discovers evidence of an ancient catastrophe. Ken Tankersley and his team dig up a layer of burnt material in the soil. It dates to when the Clovis and the mammoths vanished. To archaeologists, this distinctive carbon-rich layer, called the black mat, indicates intense burning, a sure sign of a destructive event.
Beneath this layer, we have evidence of large mega mammals. Above it, there's none whatsoever. This mat was deposited in a very quick and sudden event. Beneath it, you have evidence of Clovis people. Above it, you have absolutely none. The real mystery is what happened at this very time.
What catastrophe caused this black mat? Tankersley searches inside the black mat and uncovers the bone of a wild pig, known as a peccary. It tells a disturbing story.
This particular bone has not seen air in 13,000 years.
The bone shows signs of extreme burning.
We know this burning is not the result of cooking. These animals were larger than I am, and to take a human body and a natural fire, you have to burn the body for days. This type of burning clearly came from a very intense, very fast burning, a single event fire, if you will.
Did an asteroid cause this deadly blast of heat? If it did, there is a vital piece of the puzzle missing. There's no evidence of a crater. This leads to a disturbing possibility. Could an asteroid be big enough to destroy an entire culture? Yet so small, it leaves no trace. Around 50,000 years ago, a small 130-foot wide asteroid smashes into the desert of Arizona and creates Meteor Crater. An impact this size could wipe out a major city. But this isn't the last time Earth was hit by a small but deadly asteroid. We're realizing that Earth is far more vulnerable than we once imagined. And some devastating impacts have left almost no trace. Archaeologist Ken Tankersley has found a black mat, evidence of an extreme heat event in a layer of rock dating back 13,000 years. The same time that the Clovis culture, one of the earliest in North America, abruptly and mysteriously vanished. Is an asteroid responsible? New research at sites across the United States also uncovers the black mat layer of burnt material, all dating back to the same time. The chemical analysis is compelling, but Tankersley wants to be even more certain. He returns to the Sheridan Caves in Ohio to take further samples. At the University of Cincinnati, an electron microscope takes a close-up view. Tankersley magnifies the tiny sample 10,000 times. He spots compelling evidence of a devastating asteroid impact. Detonation diamonds.
What's kind of tantalizing here is the possibility that these are associated with a cosmic event, if you will. Detonation diamonds are the result of a strong impact from either a large meteorite, an asteroid, or slice of comet.
Major asteroid impacts have shaped history more dramatically than ever imagined. It seems increasingly likely that an asteroid is the reason for the Clovis culture's disappearance 13,000 years ago.
In geological time, 13,000 years ago is yesterday. The implications for us living on the planet today, we always think it's not going to happen to us. The reality is when it's going to happen next.
No one has ever found a crater from this event. So the question is, how big was the asteroid that caused this catastrophe? Asteroids are mostly composed of rock and metal, debris left over from the formation of the solar system 4.5 billion years ago. Thousands of these objects orbit near the Earth, some as big as mountains, others smaller than a speck of dust. The size of the asteroid that may have ended the Clovis culture is a mystery. One scientist thinks he can find the answer. Professor Peter Schultz of Brown University starts with one vital piece of information. The Clovis culture ended during an ice age. 13,000 years ago, North America is partially covered in a layer of ice up to a mile thick, the Laurentide Glacier. So the question is, what happens when an asteroid slams into ice rather than land? Schultz suspects the asteroid would leave a crater in the ice, a crater that might eventually melt, hiding all evidence of the impact.
The fact is, ice was there, and there's no reason why an impact couldn't hit there as well as any other place.
Schultz tests his theory in the vertical gun range at NASA Ames Research Center outside San Francisco. The vertical gun is unique. It can fire projectiles at 13,000 miles per hour, equivalent to the speed of a real asteroid. Schultz must find the exact ratio of asteroid size to ice thickness to cause a devastating explosion, but leave no crater. He uses a tiny glass bead in place of an asteroid and a half-inch sheet of ice for a mile-thick glacier. The experiment will tell Schultz how much damage a half-mile wide asteroid would cause.
We got about 3/4 of an inch of sand in there. We're going to be firing a projectile about a 1/4 inch across, but the question is whether or not it's going to penetrate all the way through.
An asteroid colliding with Earth smashes into the atmosphere. Friction superheats it as it plummets through the air. Schultz simulates Earth's atmosphere by filling the chamber with argon gas. The gun will fire the projectile at almost 4 miles per second, the equivalent speed of most asteroids.
Every time you do an experiment, you learn something brand new. I love surprises, and invariably we have a surprise.
Could an asteroid be small enough to leave no crater, but big enough to devastate large parts of North America? It's a pressing question. The solar system is full of smaller asteroids. During the last ice age 13,000 years ago, an asteroid may have incinerated parts of North America, but left no crater. Scientists are trying to find out how an asteroid could be big enough to wipe out an entire culture and yet leave no imprint. Peter Schultz uses the vertical gun range to test what happens when a half-mile wide asteroid hits a mile-thick sheet of ice.
Oh! Pow! Oh my gosh! That's gotta hurt. Did you see that? Look at that stuff. Man, that hurt.
A glass bead enters the chamber at 13,000 miles per hour. When it hits the gas simulating our atmosphere, it burns and then explodes. A fireball smashes across the ice.
This is when you say, oh crap. It's coming for you. You can't even hear it because it's going faster than the speed of sound.
The experiment shows that a half-mile wide asteroid hitting a mile-thick ice sheet would have catastrophic consequences.
Oh wow, there's no crater. You don't even know that it happened. Let me go ahead and take some pieces out, okay? Here's where one big mass hit. You can see the little pit in there. If the ice hadn't been here, we would have formed a crater about that big. The ice acted like a flak jacket. You know, once this goes away, once the water goes away, you can't tell that anything was here. That's remarkable.
The after effects of the impact would have been felt as far away as Europe. But the asteroid itself leaves no crater.
All you need is an object about a half mile impacting into that. It might have formed a crater 20 miles across, but when the ice disappeared, melted, went away, you might completely remove the evidence. It's kind of like a perfect cosmic crime.
The asteroid that may have ended the Clovis culture could have been just half a mile in diameter. An estimated 1,000 asteroids of around this size hover near to Earth at this very moment. Scientists decide to look at other more recent impacts in order to reevaluate their size. One of the most famous and powerful recent asteroid impacts is known as the Tunguska event. June 30th, 1908, an asteroid explodes over Tunguska, Siberia with the force of 1,000 atom bombs. Tunguska is so remote that it takes 19 years for scientists to mount an expedition to examine it. The team brings survey equipment to record the devastation. The blast tore 60 million trees out of the ground. 800 square miles of Siberia, an area 1.5 times the size of Oklahoma City, are flattened and scorched. There is no crater. The asteroid exploded before it hit the ground. The size of the asteroid remains a mystery for almost 20 years. Then in the 1950s and 60s, impact specialists attempt to simulate the strike using data from nuclear tests. Some scientists estimate the Tunguska asteroid was up to 600 feet across. That estimate has been reduced to around 200 feet. In 2007, Dr. Mark Boslow reanalyzes the data using a supercomputer. He thinks the asteroid is much smaller.
Most of us had been thinking that it was an asteroid, came streaking in, it got down to about 5 miles above the surface and exploded with an energy of between 10 and 20 megatons. So we knew roughly what the wind speeds and what the thermal effects would be on the ground for an explosion at that height and that magnitude. And what was observed at Tunguska was consistent with that.
But this theory assumes a nuclear weapon and an asteroid impact in the same way. A nuclear weapon explodes from a single static point. But an asteroid is different. It's moving fast. So when it explodes, the energy it releases keeps moving, causing even more destruction.
When it explodes, it vaporizes, it begins to expand. It's very much like a nuclear explosion, except it's got a lot of mass and it just keeps on moving.
So the explosion over Tunguska spread out across the landscape.
We realized that even though it explodes at this high altitude, that explosion continues downward. All that hot rock, all that vaporized asteroid material continues downward, and finally it slows down and finally stops a few miles above the surface. The blue color here represents the shock wave, that blast wave that carries mechanical energy down. So that's very high wind speeds, hurricane force wind speeds. So when that hits the ground and sweeps across the ground, that's blowing trees down.
The old model assumed a stationary explosion. That meant a 200-foot asteroid. The model was probably wrong. A moving object could be small and still cause that much devastation.
The Tunguska event could have been caused by an asteroid as small as 100 feet in diameter.
Boslow's findings sent shockwaves through the scientific community.
There are many more smaller asteroids in Earth-crossing orbits than there are larger asteroids. Therefore, if Tunguska was from a smaller asteroid, a Tunguska-like event is more frequent than we had previously thought.
Scientists once thought an asteroid around 600 foot wide caused the obliteration of Tunguska. A rock that big hits Earth once every few thousand years. Now they've downgraded the size of the Tunguska asteroid to just 100 foot across. These hit on average every few hundred years, and the last one we know of was in 1908.
The most likely scenario for a big destructive impact event is from a Tunguska-sized object.
It's a game of chance. Another Tunguska-sized asteroid might not strike for another 100 years, or it might strike tomorrow. Luckily, the Tunguska asteroid hit in an unpopulated area. In today's world, we might not be so fortunate. The question is, what can we do to protect ourselves from asteroids, big or small? In 1998, the US Congress instructs NASA to take action. It sets up the Space Guard Survey to identify and track any near-Earth asteroids that pose a threat to our planet. The first step is to identify the asteroids at least 3,000 feet across, the ones big enough to cause massive destruction if they ever hit Earth. So far, 1,100 asteroids this size have been located. The Catalina Stewart Observatory at the University of Arizona is part of this Space Guard network. Asteroid hunter Ed Bayshore and his team comb the skies for these giant asteroids.
Essentially what we need to do is we need to image an area on the sky 4 times over the course of about 40 minutes.
The computer takes 4 telescope images of the same patch of night sky. The stars stay still. But near Earth objects, the asteroids, move through frame.
So for instance, here's the first image of a field that we just observed. There's the second image, there's the third, and there's the fourth. When we start it blinking, we can see that we have an object right here in the field. As it turns out, that is probably an NEO by the way it's moving.
But what about the smaller asteroids? The ones we think wiped out the Clovis culture or exploded over Tunguska? Right now, Bayshore doesn't search for them at all.
There's many more objects that are smaller. And just because they're smaller doesn't make them not dangerous. In fact, we think the objects around 300 feet in diameter and larger, which are much more numerous, may actually represent a considerable threat.
Now, space scientists are determined to track these smaller asteroids. Among them is a man who is no stranger to the hazards of outer space, former Apollo test pilot Rusty Schweikert.
Now, it's very important that we start looking for these smaller ones because they hit with much higher frequency. From 100 to 150 feet in diameter and larger, we can start having serious effects on the ground. They are huge in terms of natural disasters.
The smaller the asteroid, the harder they are to find. They move at around 50,000 miles per hour in orbits that are extremely hard to track.
Because we've only been looking for the biggest ones up until this time, our telescopes really aren't adequate to give us the information, the early warning that we need on the smaller objects.
Tracking small asteroids requires specialized telescopes. These are still years away from completion. But occasionally, astronomers get lucky. In 2004, they pick up a moving object in the sky. Closer inspection reveals it's an asteroid, and it's 900 foot across. Researchers name it Apophis, after the Egyptian god of evil and destruction. It is big enough to destroy an area almost the size of Texas, and it is coming our way. In 2004, at the Kitt Peak Observatory, Arizona, scientists spot a new and relatively small asteroid. It looks like it is on a collision course with Earth. It is called Apophis, and it's 900 feet across. Around 10 times the size of the asteroid that created Meteor Crater in Arizona. At the Massachusetts Institute of Technology, Dr. Richard Binzel tracks its trajectory.
An impact the size of Apophis in terms of the immediate damage would be regional, roughly the size of France in terms of its immediate catastrophic effects.
Based on initial observations, researchers believe it has a relatively high chance of hitting Earth in 2029. The asteroid poses a real threat. Binzel needs to discover what Apophis is made of. He studies the asteroid via a remote link to a telescope in the Mauna Kea Observatory, Hawaii.
The instrument we're using is a spectrometer. The different minerals that are present in asteroids have very critical absorption bands, or very fingerprints, if you will, in these wavelengths of light that let us distinguish between different kinds of compositions, different kinds of minerals.
No two asteroids are the same. Most are solid, but some are loose piles of rubble. The majority are made of rock, but some are composed of metals and other materials. Apophis turns out to be mostly made of chondrite, a type of rock.
We think that Apophis is like this type of meteorite. It's an LL chondrite meteorite. And the beauty is that we can measure the properties of this meteorite in the laboratory. And if we scale this meteorite up to the size of Apophis, which we think is about 900 feet across, the mass of Apophis is about 20 million tons. The energy that it would have if it hit the Earth is about 375 megatons, the kind of energy we usually talk about with nuclear arsenals. And that's more than 20,000 times the energy of the blast at Hiroshima.
With the asteroid's speed and orbit mapped, researchers can predict its trajectory more accurately. New data suggests that the 900-foot asteroid is headed this way in 2029. It will miss Earth by just 18,000 miles. A near miss in astronomical terms. But if Apophis had been on a collision course, what could we have done? The most obvious solution is a nuclear bomb. The theory is that a blast could shatter it into pieces. But this approach is risky. blast fragments could continue on a collision course with Earth. And to make matters worse, they are now radioactive. Instead of eliminating the risk, a nuclear explosion could increase it. Earth could get hit by a cosmic shotgun blast, resulting in even more widespread devastation. One scientist alarmed by this scenario is Dr. Massimiliano Vasile of the University of Glasgow in Scotland.
What could happen is that the shock wave due to the explosion of the outer crust fragment the asteroid. So it might be that basically we have not just one asteroid on the collision course with the Earth, but we have 2 or 3 asteroids.
Scientists are racing to find a better solution. They have suggested attaching rocket engines to push the asteroid off course, or even solar sails to pull it into a different orbit. These are possibilities, but they sound like the stuff of science fiction. Researchers are putting their weight behind a more feasible solution: knock the asteroid off its collision course. The project's code name, Don Quixote. At the heart of the team is space mission analyst Chris Saunders from Kinetic Labs, England.
We're simply going to try and hit the asteroid and deflect it out of the way.
The theory is that a powerful strike delivered by a probe could knock the asteroid off its course, like a game of cosmic pool. Don Quixote is a 2-stage spacecraft made up of the impactor and the orbiter. The ion engine powers the orbiter to its target. Solar panels create an electric field which ionizes an ultralight fuel load of xenon gas, ejecting ions from the engine to thrust the craft towards the asteroid at up to 200,000 miles per hour. The aim is to catch the asteroid as far away from Earth as possible, so that even a tiny push will move it off course. The observer locks into orbit around the asteroid and guides the impactor to an inch-accurate surgical strike.
It would move the asteroid's orbit by maybe 50 to 100 meters. That would be enough for the asteroid to safely drift past the Earth.
If astronomers locate an incoming asteroid early enough, Don Quixote might be able to deflect it. But it's untested technology with a huge margin of error. Most scientists agree a backup plan is essential. To defend Earth from an asteroid strike, scientists have an ingenious and radical approach. Use an intense ray of light to vaporize part of the asteroid's surface, creating a jet of gas that will move it off course. It's a good theory, but right now the only place Massimiliano Vasile can test it is in the lab. He uses the Industrial Laser Lab at Glasgow University to gauge how much light energy it takes to move an asteroid.
We can see the effect of the light of the laser that basically was burning the rock. This is what we expect would happen in space when we focus the light of the sun on the surface of the asteroid. The effect that I obtain is exactly as if I had a rocket engine attached to the asteroid, but the difference is that the engine is the asteroid itself. This is in fact one of the most effective ways of deflecting the asteroid.
But shifting a full-scale asteroid would take a lot more light than an industrial laser. Luckily in space, we have a huge power source available, the sun. Vasile proposes using mirrors to focus sunlight on the asteroid, enough to vaporize its surface just like the laser. But moving a 1,000-foot asteroid requires a mirror so large that no rocket is big enough to carry it into space. The solution? Use several small ones at once.
We propose to have a swarm of satellites, each one carrying a smaller mirror.
The mirrors would be around 60 feet across and precisely shaped to concentrate the solar energy, creating that vital jet of vaporized rock. Whatever system scientists end up using, the key is to catch the asteroid as early as possible. Astronaut Rusty Schweikert thinks it's vital to be prepared.
Even you and I driving our car, you and I typically have one chance in 10,000 that we're going to have an accident tomorrow if we're driving tomorrow. And because of that, we buy insurance. We're driving around the solar system on our planet totally uninsured. Why?
Someday, humanity will likely face another asteroid, like the one that exploded over Tunguska, or wiped out the Clovis culture. An asteroid just 150 feet across could kill tens of thousands of people. And we still don't know enough about them. The dangers and our lack of knowledge became all too apparent in September 2007. Carancas, Peru. Local people noticed strange lights in the sky, followed by a huge explosion. Villagers stumble on a 50-foot wide crater in the highlands. Locals claim it is caused by an asteroid, but not all scientists are convinced. Impact specialist Peter Schultz thinks it's a hoax.
My immediate reaction was, are you kidding me? This has really happened? It can't really be something that actually got through the atmosphere. This is science fiction. And the first pictures that came out, it looked like a B movie with this crater where Superman was going to walk out.
Schultz is disturbed by the size of the crater. It's tiny. An asteroid that small should never have made it through the Earth's atmosphere. It should have burnt up on entry. September 2007, a fireball blazes through the skies of the Peruvian highlands. It crashes to Earth near the village of Carancas in southern Peru, leaving a crater 50 feet in diameter. Eyewitnesses are mystified. At first, they think they're under attack.
We looked up at the sky and saw a smoky trail. First we thought it was a military plane. Then we saw that the object was approaching the ground, heading south. The worker said to me, "I think that plane is out of control." We were really scared. Even animals are running away due to the loud noise.
One explanation is an asteroid strike. But how did an asteroid so small survive entry into the atmosphere? It should have disintegrated before impact. Peter Schultz, one of the world's leading impact specialists, travels to the site to investigate.
I heard the stories in the media, I saw the pictures, and I thought, oh my gosh, I've got to go there.
The impact has blasted chunks of Earth into the air, damaging a building 150 feet away.
Wow. Oh, jeez. Oh, my gosh. Wow.
Whatever caused this crater was powerful enough to blast 100 tons of soil across the landscape.
This is clearly the pre-existing soil. Everything was just simply turned upside down over this.
This has all the hallmarks of an asteroid crater, But Schultz is skeptical. He needs to find a fragment to prove it. He exploits a common characteristic of this kind of asteroid, its magnetism. The metallic fragment and the shape of the crater convinced Schultz that this was an asteroid strike. But how big was this asteroid? Eyewitnesses tell Schultz the angle of impact. Now if he can discover the speed, he should be able to discover the size. At the NASA Ames Research Center, Schultz examines the fragment of asteroid under a powerful microscope. It reveals the true story behind the impact.
The fragments were deformed. They were fractures, and they were in a pattern that happens at around 3 to 4 miles per second, almost 5 times the speeding bullet.
Schultz now has all the clues he needs to figure out the size of the asteroid.
From those pieces of information, the angle and the speed, we can determine how big it was. And it's probably somewhere between 3 feet and 6 feet.
It's an extraordinary discovery. Up until this moment, scientists believed rocky asteroids this small burned up before they hit the ground.
Here we have a puny thing, only about 3 to 6 feet across, that somehow made it to the surface. This shouldn't have happened. This just shouldn't have gotten through the atmosphere. In this case, it made it through. It not only made it through, but it hit hard.
How it got through exactly is still a mystery, but the fact that it did is alarming. If a tiny asteroid like the one that hit Caracas strikes a crowded city, it could potentially kill dozens, if not hundreds of people.
Will it kill people? Yeah. The clock is ticking. It's coming.
This is not one of those giant things. This is the type of thing that if it happened in New York, it would have caused some serious damage. It probably would have gone right through the ceiling of a tall building and gone through about 4 or 5 floors before it rested.
In Peru, we were thrown a hypervelocity curveball.
Rusty Schweikert believes that now is the time to take the threat from smaller asteroids seriously.
A hurricane, we can't prevent. A flood, we can maybe do some things to prevent. We can certainly mitigate against these things. But preventing is an unusual opportunity in a natural disaster. We can prevent this from happening. If we do our work with near-Earth objects, we can prevent asteroid impacts from ever happening.
There is little doubt that an asteroid will someday threaten the Earth. The question is, will we be prepared to deal with it in the not-too-distant future?
Planet Earth. 4.5 billion years of evolution. It's all going to end. Titanic forces are already at work that will destroy the world as we know it. Scientific investigators take us on an epic journey into the future of the Earth, where apocalypses will wipe out all life and destroy our planet. This is the countdown to the end of the world. Seven and a half billion years from now, Earth will be consumed by fire and vaporized. But by then, it will be unrecognizable, a lifeless alien world. Long before its final moment, our planet could be struck by no less than 7 great catastrophes. One by one, They will turn the jungles into deserts, reshape the continents, and boil away the oceans. Other disasters will destroy the atmosphere, annihilate the animals, and destroy every plant. These are just the catastrophes we can predict. And what of mankind? We could be the first to go. This is the story of the death of the Earth. The first threat to life on Earth comes from the heavens. Right now, a lump of rock and metal, 6 miles wide, traveling at 17 miles per second, could be headed our way. It could strike next week, next month, or next year. But whenever it does, there will be little we can do. We would have very little warning before that threat turns into an asteroid impact. Earth has always been in the firing line.
It could happen tomorrow. It could be 100 million years from now. But it's not a matter of if, it's when.
300 million miles out from the sun, beyond Mars, is the asteroid belt, the rubble of a planet that never formed. 750,000 massive lumps of rock, more than a half a mile across. It's an inexhaustible source of planetary ammunition that gets knocked out of the belt and sent spinning across space. NASA astronomer Professor Don Brownlee knows a lot about asteroids. The record of the devastation they bring is hard to miss.
Just look at the moon in the night. You see it's covered with craters, huge craters. Impacts that happen to all the planets that have happened for billions of years throughout our history. So this will happen.
It already has. 65 million years ago, an asteroid 6 miles wide slams into the Earth. The impact throws up millions of tons of rock thousands of feet into the air, fusing sand into glass in a split second. This one impact wipes out the dinosaurs, a species that had endured for 160 million years. So what are the odds of this kind of asteroid strike happening today? Using the visible impact record on the Moon and planets like Mars and Mercury, Brownlee has come up with an answer.
The frequency of impact of a 10-kilometer object from space, a comet or an asteroid, of the kind that wiped out the dinosaurs 65 million years ago, is on the average about 1 every 100 million years.
When it strikes, it instantly vaporizes every living thing for miles around. The sheer force of the impact buckles and cracks the Earth's crust, creating powerful earthquakes. The force of the winds whips up waves, pushing powerful tsunamis onto the land. Within a few days, the dust cloud blocks the sun, plunging the planet into freezing darkness. An endless winter that would last for more than a year. Hidden within the dust is something far worse. A sudden overdose of nitric oxide destroys 85% of the ozone layer. As the dust finally settles, the lack of ozone allows damaging ultraviolet rays to reach the surface, harming billions of people and killing plants and animals with lethal doses of radiation. By the end of that first year, at least 70% of all life would have been destroyed. Those that live underground or hibernate stand a better chance. This is what killed the dinosaurs. And one day, the same thing could happen to us. Not knowing when the next asteroid will strike makes planning difficult and worrying pointless. There is worse to come. Even if we could plan for the next catastrophe, it won't make any difference. Ice sheets several miles deep pushing down from the poles will be unstoppable. A global ice age is coming. How do we know? It has happened before, and one of the first clues was pulled from the La Brea tar pits. To find an ice-loving woolly mammoth was a big surprise. To find it in the heat of California was a mystery. Could California have once been covered in ice? Could it happen again? To find out, scientists need a record of changes in the climate, stretching back tens of thousands of years. It turns up in the layers of sediment at the bottom of the ocean. Marine geologist Professor Peter Domenical is searching for clues to Earth's frozen past.
Deep sea sediments are really unique archives of past climate change because the sediments in the ocean accumulate very continuously and very slowly over time. So they present us with this kind of history book of past climate change.
These tiny chunks of rock in the sediment hold the answer to the USA's frozen past and to its future. Deposited 10,000 years ago, how they got here is astonishing.
Icebergs carry all these rocks and they hold them inside the iceberg and then they melt. As the iceberg melts, it drops its load. And that's how we find these big pebbles out in the middle of the ocean.
Icebergs once floated off the coast. As the bergs melted, the rocks they carried from the north sank to the seafloor. 10,000 years ago, much of North America is in the grip of an ice age. But what causes a big freeze? The answer isn't found beneath the geologists' feet, but over their heads, in outer space. The Earth orbits the Sun in an ellipse that gradually changes shape over time. The tilt of the Earth to the Sun also changes. Calculations suggested that the interaction of these changes could flip the climate from warm to cold and back again. It's called the Milankovitch cycle, after the man who discovered it. His orbital calculations showed that the Earth flipped from ice age to warmth 10,000 years ago, the exact age of the sediments Domenical has found.
It was shocking when the evidence came out that there was this very close correspondence between the astronomical calculations and then really the geologic record. People were just blown away.
But what about the future? The orbital effect is called the Milankovitch cycle because it happens over and over again.
We're well on our way, actually, into the next ice age. That's something most people don't really fully appreciate. Climate was significantly warmer 5,000 and 10,000 years ago, and then we've been gradually headed into this much cooler climate.
Domenical believes the Earth will be plunged into another global ice age within 30,000 years. If the last one is anything to go by, the next will be worse. Because in the last ice age, there were just 5 million humans. Now, there are 6 billion. Could we all survive? Ice sheets 2 miles thick could cover the land. Cities like London and New York may be buried beneath thousands of feet of ice. Global sea levels could drop 400 feet as water is locked up in ice. Freezing temperatures might last 100,000 years. The food chain collapses. Plants die as they are smothered by ice. Herbivores can no longer find food and die out. As civilization collapses and food and shelter become scarce, our base survival instincts kick in. Dr. Erwin Redlener at Columbia University is an expert in how humans react to catastrophic events. The bad news is, many won't make it.
The major challenges will be to how to keep ourselves from killing each other because of a natural event like a new ice age. Enormous migrations of people trying to escape from the extreme conditions have the potential of causing a tremendous amount of deadly competition for resources, for food, for water, for power.
Billions of people could perish as vast areas of available land are swallowed by ice. But many humans will survive the big freeze in belts of green, north and south of the equator. Here, agriculture will continue, but not enough to support the billions who will now begin a battle to control it.
I think we are hardwired on a genetic DNA level to seek survival at almost any cost. And I think there's pretty good examples of that. People who were prisoners of war and people lost in hostile environments.
In a few green areas, humans will survive, but the population will be greatly reduced. Civilization as we know it will change forever. And the next ice age is unlikely to be the last. The great ice sheets will continue to advance and retreat, devastating life and civilizations. 250 million years in the future, it gets worse. Life will face an even greater threat and be pushed to the very brink of extinction. The seas will die and the land will become desert. $250 million years in the future, having survived ice ages and perhaps even asteroid strikes, there now comes an even greater threat. The surface of the planet is completely unrecognizable. Life is being pushed to the brink of extinction. This terrifying vision of the future is caused by the same powerful forces that shape the Earth today.
Plate tectonics was one of the two major scientific advances of the 20th century. It allowed us to get an understanding that the Earth is really much more dynamic than we ever suspected.
It reveals that the Earth's surface is made up of a series of massive continental plates that are in constant motion. Where they collide, huge mountains are driven up and massive volcanoes pour out liquid rock. It shapes the face of our planet. Armed with this new information, the geological record opened up like a book, revealing that 250 million years ago, all the continents were united to form a single supercontinent we call Pangaea. This was a hot, brutal world ruled by dinosaurs. Could future movement of the tectonic plates transform the Earth once again into a single vast landmass?
We now know how the plates are moving far more accurately than ever before, and so it became tempting to look into how this might develop if we projected these motions a few million years into the future.
According to Livermore's model, 250 million years in the future, a new supercontinent will form. Africa plows into the Middle East as Antarctica and Australia fuse together. One vast landmass surrounded by a giant ocean.
We end up with a supercontinent which is primarily in the northern hemisphere and a southern hemisphere which is mainly ocean. This will give us a range of habitats within the supercontinent quite different from anything that we see at the present time.
With much of the land hundreds or thousands of miles from the ocean, rainfall becomes non-existent. No plants grow, and as the land absorbs the heat, temperatures soar. It turns to desert.
If we were looking down on the future supercontinent, what we're likely to see is something really rather like the interior of Australia.
250 million years in the future, this new world will be mostly desert, covering over half of the land, so hot and dry that few plants or animals survive. 80% of the species we see today could be wiped out. Those that do survive will have to adapt to less water, less food, and rising heat. Our distant descendants might try to take refuge in the coastal regions. But even here, there's no escaping the dangers of this new world.
Around the edges here, we're probably going to see continuing volcanism, continuing earthquakes.
The tectonic forces that pushed the supercontinent together are still at work. Now they begin to buckle and split the land at its weakest points. The result is massive earthquakes. Lava exploits these new cracks and bursts out, forming chains of volcanoes. Molten rock spreads over thousands of miles, incinerating every living thing in its path. Life on the land will be tough beyond our imagination, causing mass extinctions. But this is nothing compared with the devastation facing life in the new superocean. In 250 million years, a single supercontinent will dominate the face of planet Earth. It has happened before. By exploring what happened back then, we now know that this single landmass could have a devastating effect on the oceans in the future. A lethal dose of carbon dioxide may cause a mass extinction, which could wipe out 96% of life in the sea. But where will this killer carbon dioxide come from? The biggest natural CO2 producers on the planet are well known, and the supercontinent of the future will have plenty of them. Volcanoes. To understand how the carbon dioxide from volcanoes leads to mass extinction in the oceans, Dr. James Barry has been studying what happens to one particular creature called a brachiopod during similar events.
Oceans became much more acid due to all the CO2 that was released by volcanic action over 100,000 years. And that increased acidity of the ocean has caused not only brachiopods, but many other types of animal life to go extinct.
Dr. Barry is trying to understand exactly what happens when carbon dioxide levels suddenly shoot up. Among the first to feel it are shellfish.
These brachiopods are a curiosity. They're one of the earliest sort of real animal life forms that evolved on this planet. 400 million years ago, they were one of the most dominant forms of life on the planet. But they went from 30,000 species down to about 300. They're the poster child for how to go extinct.
Brachiopods had survived everything the Earth could throw at them for hundreds of millions of years. Yet it was volcanic eruptions on land that wiped out 99% of brachiopod species in the sea. Barry's research reveals how. Brachiopods are highly sensitive to carbon dioxide levels. The excess CO2 from volcanoes dissolves in the water, making it acidic.
Once it enters the ocean, it combines and reacts with seawater to form carbonic acid. And that changes the balance of chemistry in the ocean.
As the sea becomes more acidic, the brachiopods die out. In 250 million years, the hard shells of all marine invertebrates dissolve in the acidic water. As their inhabitants die, a big link in the food chain collapses. Their predators starve, and the lack of food goes right to the top of the chain. At the same time as the food chain is collapsing, another brutal consequence of a single supercontinent will be reaching its endgame. 80% of marine species live close to the coastline. With all the land locked up, there's less coast to go around. Competition for the prime real estate gets fierce. The coastline of the future supercontinent could be 70% less than it is today. So the next supercontinent will be deadly. In 250 million years, an arid desert on land and an acid ocean means a mass extinction that will make the death of the dinosaurs look like a sideshow. But amazingly, some plants, some animals will survive. Those that can adapt. Creatures like snakes and spiders that thrive in the heat. Low hardy bushes and types of cacti may be able to evolve. Life will endure for 1 billion years to come. It's only then that the final extinction of life on our planet begins. The end of all life on land. 1 billion years in the future, the world is going to get hotter. All stars, like our sun, go through a cycle of life and death. Today the sun is middle-aged, but in 1 billion years, it will be that much closer to death. As it burns through the remainder of its fuel, internal processes will cause it to expand, bringing its surface ever closer to the Earth. The temperature will soar. It is now 86 degrees and climbing. For mankind, another 18 degrees higher, and we will have reached our physical limit. Blood thickens, strokes and organ failure follows. Sometime in the next 1 billion years, humanity will cease to function. At this point, we will have disappeared forever from the face of the Earth. But other kinds of life will be able to survive. Here at the California Academy of Sciences, Professor Lynn Rothschild searches the history of past extinctions for examples of what creatures might be able to survive in a world twice as hot as today.
What I'm holding here is an ammonite, and these were extremely successful group of invertebrates. They were wonderful predators, and they went extinct at the end of the Cretaceous. Not their fault. They were wonderful at the time, but they went.
As the sun expands and the world heats up, it all comes down to luck. If you happen just by chance to be better suited to the new world, you'll make it. If not, it's just bad luck. And in the brutally hot future Earth, we already have a fair idea who's going to be lucky.
We see animals like scorpions, like we have here, spiders, maybe some snakes that come out at night. And these are so well adapted to living in these hot, dry environments because they prevent water loss. They do everything they can to keep water inside their bodies. They stay nocturnal.
Only the most extreme adaptations can survive. But as conditions become worse, life on land heads toward its final moments. It begins with the plants. Atmospheric scientist Professor James Casting is one of only a few people in the world to have figured out what happens to the plants in 1 billion years from now. He's discovered that a drastic fall in CO2 will wipe most of them out.
CO2 will drop by a factor of 1/2. That will wipe out 95% of the plants on Earth.
Geological processes are at work today that absorb carbon dioxide and dump it in deep ocean sediments. But like all chemical processes, the higher the temperature, the faster it works. Supercharged by the hot Earth 1 billion years from now, it wipes carbon dioxide from the atmosphere.
It will drop down below the level required to sustain plant life. And that's the fundamental food source on Earth. I mean, carbon dioxide is the food of life. It's what makes photosynthesis work. And with CO2 gone, it's a very different world.
Deprived of CO2, plant life suffocates and dies. The last remnants of our green Earth turns brown and dead. One vast desert covers the land.
It's really hard to imagine a future without any plants. I guess the best way to imagine it is to go up into the desert. In a way, it's a very beautiful environment, but it is very barren, and it doesn't seem like home.
Without plants, the food chain collapses. The plant eaters starve, and their predators follow. Animals, insects, reptiles, and mammals. For life on land, everyone's luck has finally run out. There is only now one place on the entire planet that does continue to support life: the oceans.
If you think about why life both originated in the ocean and probably will be forced back into the ocean in the future, it's because the ocean is far more stable than land. If you go out into the desert in the middle of any continent here, the summers are sweltering and the winters are frozen. During that same yearly cycle, the temperature right offshore here nearly stays the same year-round.
But a billion years in the future, as the dying sun swells and the temperatures rise, the oceans begin to evaporate. As the water level drops, they become more and more salty. To understand what the oceans of the future will be like, Professor Rothschild has come to these salt ponds outside San Francisco, where seawater is evaporated to produce salt.
What happens here, and you'd imagine would happen on the Earth, is that as the concentration of salt goes up, 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 many of the organisms that we're familiar with, fish and kelp and algae and manta rays and so on, drop out.
It is the end for life in the oceans as we know it. Whales, dolphins, jellyfish, coral reefs, pretty much everything. All gone, unable to survive in the increasing saltiness of the water.
And at some point, you're left with brine flies, a few little worms, and some of the microbes that you see here. And at the very highest salt concentrations, about 10 times the salinity of the ocean, you only end up with organisms called halophile.
It is the halophiles, tiny organisms that thrive in high salt environments, that give the water its red color. This color is no accident.
Now, during the summer, we tend to get tanned. I've been in the pool, I look a little tanner than I would in the winter. Well, these organisms also have to protect themselves from a very strong sun, ultraviolet radiation. And so instead of tanning, they tend to produce a lot of red pigments, carotenoids. These are the same kind of compounds that you see in tomatoes and carrots and so on. And this orangey red pigment helps protect these organisms from the very high sunlight.
With a blazing sun filling the sky and temperatures rising, only these incredible survivors called extremophiles can take it. 1.2 billion years from now, all other life is gone.
As the Earth becomes a very hostile place, we're back to having a world that's only populated by microbes, very much the way it was during the early evolution of life on Earth.
Extremophiles clinging on at the ragged edge of survival in the last remnants of the ocean. The final hammer blow that will end all life is now just around the corner. 1.2 billion years from now, plants and animals have been wiped from the surface of the Earth. Only microbial extremophiles survive in a rapidly evaporating, increasingly salty ocean. For the oceans, time has finally run out. The brightness of the expanding sun boosts average global temperatures to a blistering 100 degrees, nearly double than today. Professor James Casting is investigating the devastating effect this has on the oceans of the future.
Well, we think that the Earth will start to lose its oceans when the sun gets about 10% brighter than it is today.
His findings confirm evidence gathered by Apollo astronauts in 1972. Hydrogen is escaping from the Earth. Water is made up of 1 part oxygen and 2 parts hydrogen. So what the astronauts were seeing was the infinitesimal loss of the oceans into space. Today, this amount is nothing serious, but 1.2 billion years in the future, when the temperature is 100 degrees, the process goes into overdrive. Faster evaporation now saturates the air with water. As this water rises to the top of the atmosphere, ultraviolet light from the sun splits it into its 2 component parts, oxygen and hydrogen. The hydrogen is so light, it floats off into space, lost forever. What casting discovered was that from full to empty, the whole process of losing our oceans could take less than 200 million years. Without water, life cannot exist. So to find out when this will happen, he had to look at a planet not unlike the Earth that lost its oceans in the same way.
Well, I got interested in the future of Earth's oceans by working not on Earth, but on Venus.
Physically, Venus is almost a twin of our planet. And billions of years ago, it might have been even more similar.
May well have had liquid water on its surface at one time, just as the Earth does now. But it was too close to the sun. It lost that water by what we call a runaway greenhouse. It's likely, in my opinion, that Earth will follow the path of Venus at some point in the future.
Studying Venus helped casting estimate when we will start to lose our oceans. The answer came as a shock.
Well, up until we had worked on this problem, many scientists thought that the Earth would retain its oceans for at least another 3 or 4 billion years. But we were able to show that bad things start to happen much earlier than that. The oceans could be lost in 1.2 billion years.
With the water gone, dry salt crusts like these are all that will remain of the Earth's magnificent oceans. Is this the end for life? Incredibly, a new discovery has shown that even without water, basic life forms can survive. But for how long?
Although we'd known that organisms could live in very high salt, we knew that they could also be trapped in solid salt. But what we didn't know is that while they're in the solid salt, it's more than them being in suspended animation, that they are actually still metabolically active. They're still breathing and eating and excreting and doing all the sorts of things they need to do, but at a very, very, very slow rate. So that was really an astounding discovery for us.
In 1.4 billion years, with the oceans finally gone, extremophiles will survive in the solid salt, but just barely.
These organisms will be able to survive a good deal longer in a salt crust like this, even in the absence of water. They won't be able to survive forever like that, but it'll buy them a little time.
Perhaps another few million years. In that time, their main protection will be the red color that acts as a sunblock. While they live, they will transform the way our planet looks from space.
People always think of the Earth as this beautiful blue planet, you know, the pale blue dot in the sky. But the fact is, for almost half of Earth's future history, it will be a Barbie planet. It will be covered with pink salt.
This is the Earth, 1.4 billion years from now. The extremophiles cling on in an increasingly desperate fight. But the rising temperatures as the sun brightens eventually defeat them. By 1.6 billion years into the future, the temperature has climbed to 224 degrees, far above the boiling point of water. Life finally loses the battle. The last remaining extremophile dies.
There are several poignant moments in geologic history. The Earth losing its oceans will be the most poignant of all, because that really will be the end of life as we know it. And unless we've figured out how to colonize other planets, then life will come to an end. It's a pretty sobering thought.
The time of the pink Earth passes. Our planet is reduced to a brown, featureless world. Unless we have found a foothold on another, this is the end of life in our universe. For the next 6 billion years, our dead world orbits the dying sun. Only an astronomer can see this far into the future, to the Earth's final moment of existence. Dr. Robert Smith from the University of Sussex has unraveled the Earth's ultimate fate. But his journey of discovery has taken some unexpected twists and turns. The process begins as the dying sun continues to swell in size.
The sun getting bigger will have severe consequences for the Earth, because we predict that the sun will get at least 200 times its present size.
All stars go through a cycle of life and death. Astronomers know this because they can see stars that represent every stage of life that our sun will go through. In 7 billion years, our sun will be close to death. The sun is now 1,000 times brighter, 200 times its present size, and still growing. The heat literally dissolves the face of the Earth, wiping away the last of its uniqueness.
As the sun gets bigger, the mountains will start to melt, and instead of having high mountains and deep ocean depths, everything will flow into a uniform sphere, be featureless, and very, very hot.
Earth's surface is now melting in 2,500 degree heat. The surface runs with liquid metal. Our planet is utterly unrecognizable, a totally alien world. The end is now close. But Dr. Smith's calculations revealed a last-minute escape might just be possible. $7.5 billion years in the future. The mountains and oceans have been erased from the Earth's surface. The temperature is over 2,500 degrees. It has been lifeless for 6 billion years. Now the Earth itself is about to die. At the heart of the dying sun, helium is reaching a critical stage. It's becoming so dense, its atoms so crowded, that the core is becoming explosively unstable. It now takes on its final form, a red giant, 256 times bigger than it is now. It fills the sky.
First of all, you would see the size of the sun beginning to increase. It would get redder, it would get brighter. At the moment, we're used to seeing it about the size of the full moon. Then it would get bigger and bigger, it would fill more and more of the sky, till eventually when it become a red giant, it would probably fill something like half the sky.
As the sun burns up the last of its fuel, it expands outwards. Now almost 200 million miles in diameter and swallowing everything in its path. Is this the fate of planet Earth? When Dr. Smith first tried to find out, the figures showed that as the sun gets bigger, it loses its gravitational grip on the Earth. The chain is broken, and our planet drifts off into space, potentially escaping a fiery death. It seemed that Smith had saved the planet.
It was a good feeling that we'd saved the Earth, and indeed some of the newspaper headlines said exactly that.
But then one of Smith's colleagues took another look and produced new calculations about the red giant. These seemed to suggest a radically different picture.
When we came to look at the calculations again, we realized that we'd missed something out. We realized that there was a missing effect which we had to take into account, and that's to do with tides.
What they hadn't taken into account are the tidal effects of the Earth on the Sun. The Earth's gravity will create a tidal bulge on the surface of the Sun, in much the same way as the Moon affects the rise of the ocean tides on Earth today. This bulge, in turn, creates a drag on the Earth, pulling it back towards the Sun. Smith set to work using the new data to find out just what would happen now.
We didn't know what to expect when we first put in this additional effect. We hoped that even when we put in the tides, the Earth would still escape.
Smith announced a very different set of results. The news was bad. The tidal effect chains the Earth to the Sun.
When we came to look at this problem again and put in the extra effects and realized that the Earth would in fact not survive, we decided to call our paper Doomsday.
The surface of the Earth is now nearly 2,500 degrees, hot enough to melt metal. The outer fringes of the Sun reach out to engulf the Earth.
If we try to imagine what it would look like to see the Earth disappearing, just be like that, an asteroid crushing through this Earth's atmosphere. It will burn up completely, it will vaporize, it will disappear, it will become part of the Sun, and it will be as if it has never been.
12 billion years of planetary history ends. The death of planet Earth, engulfed in flame, vaporized by the Sun, reduced to atoms.
Sort of dust to dust. But it's not such a bad fate, because those atoms, your dog's atoms, your car's atoms, they go out into space, and what do? They end up forming new stars, new planets, and maybe even new people.
It's a cruel act of fate that life-giving stars will one day go bad. Big changes are coming. By understanding how Earth worked in the past and how it works today, science is beginning to understand what the future may bring. The death of the Earth is already laid out in front of us. It's written into its geological past, and literally into the stars above us.